Yeah, hi everyone, welcome back. So we have been studying about linear algebra, right? So we have covered a lot of topics. In the last lecture, what we were studying? We were studying about null space. So just like null space, there is another concept that is eigenvalue and eigenvector, and it is very important. In your gate examination, it is very important. So in null space, what was the scenario? That said, there would be a matrix A. If I multiply my vector x with the matrix A, then what this matrix A was doing? This matrix A was mapping this vector x to 0. Then x is known to be in the null space of A. X belongs to the null space of A. So vector x being multiplied with A is going towards the null, or you can say A is mapping the vector x to null, or you can say x belongs to the null space of A. So that was the concept of null space. Here what will happen? Again I am having a matrix A. Now vector x will be multiplied with matrix A only. In the output you will receive again vector x. Sir, matrix A multiply with vector x, again in the output you are receiving vector x only. When this condition is possible? When sir A is identity matrix, right? Because identity matrix multiply with x will give you x only. But here I am not expecting the output to be x. Here I am expecting output to be x multiply with some factor lambda. What I mean to say is that let's just say I gave my input as 1, 2, 3. Then there was this matrix A, which I don't know, whatever this matrix A was there. Then at the output, what I received 1, 2, 3 multiply with 4. That means what I actually received? I actually received 4, 8, 12. 4, 8, 12. So when I saw this 4, 8, 12, I go to know that if I take 4 common, if I take 4 common from here, if I take 4 common from here, what I will be getting? I will be getting 1, 2, 3. So when I applied input x, this was the system or this was the machine, eventually it gave me 4x, right? So if this is the scenario, then x is known to be the eigenvector of matrix A. What it is known to be? Eigenvector. X is the eigenvector, and what is lambda? Lambda is known to be the eigenvalue. Okay, so lambda is the eigenvalue and x is the eigenvector. Now there could be multiple eigenvalues, there could be multiple eigenvectors. Are you able to understand this point? Let's just say there was this matrix A. I multiplied here x1. So what I received? First I multiplied x1. There was this matrix A. I received some lambda 1 multiplied with x1. Then what I did? To the same matrix I multiplied x2. What I received? x2 again multiplied with some factor which is lambda 2. Or what I did? Again there was a matrix A. Then I sent some x3. What I received? x3 again multiplied with some factor lambda 3. Right? So there could be multiple vectors like that. There could be multiple eigenvalues as well. But with respect to each vector, there will be one eigenvalue. Right? Understandable? I hope it is clear to you what is the meaning of eigenvector and eigenvalue. Is that clear? So matrix A was multiplied with vector x. Why I am calling it vector x? Because it will be a column vector, right? Just in the null space as well, this was a column vector, no? So I am saying that this is my n cross n matrix. Okay, this is my n cross n matrix. So this will be a column vector of n cross 1. So A will be multiplied with x. You will receive the vector x again multiplied with some factor lambda. The value of lambda could be anything. It could be 1 by 2. It could be 3. It could be 4. It could be minus 1. It could be minus j. It could be 1 minus 1 plus j. It could be anything. Okay. So this is the theory that is written, that let A be a square matrix. This will be a square matrix only. In the whole lecture, A will be a square matrix. Okay. The concept of eigenvalue and eigenvector is defined only for the square matrix. So let A be a square matrix and x be a non-zero vector x. So and lambda is a scalar such that Ax equals to lambda x. Then x is called eigenvector of matrix A. X is the eigenvector and lambda is known to be the eigenvalue of matrix A corresponding to the eigenvector x. Or other language, what you can say? There is another language that lambda is the eigenvalue of matrix A. Okay, and x is the eigenvector corresponding to the eigenvalue lambda of matrix A. What I am saying? X is the eigenvector corresponding to eigenvalue lambda. Because you can see here that with respect to x3, there is a different eigenvalue lambda 3. With respect to x2, there is a different eigenvalue lambda 2. With respect to x1, there is a different eigenvalue lambda 1. Okay. So all these things you don't need to care much. Basically, what you need to care? You need to care only one thing, that I sent x1, in the output I received x1 only multiplied with some factor. I sent x2, in the output I received x2 only multiplied with some factor. I sent x3, in the output I received x3 only multiplied with some factor. Is that clear to you? Okay. So x1, x2, x3 will be known as the eigenvectors, and lambda 1, lambda 2, lambda 3 will be known as the eigenvalue. Or you can say x1 is the eigenvector corresponding to lambda 1, x2 is the eigenvector corresponding to lambda 2, x3 is the eigenvector corresponding to lambda 3. Understandable? Okay. Let's solve a question. This matrix A is given. Now, with respect to this matrix A, which all eigenvectors are there? What this question is saying, which of the following vectors are the eigenvectors of A? And for each valid eigenvector, you need to tell the corresponding eigenvalue as well. So that means basically what we need to do is that we need to pick up this matrix A, then multiply this matrix A with the eigenvector. This could be possibly the eigenvector, this could be also possible eigenvector. Then we need to multiply our matrix with these vectors, and we need to see what results we are getting. If we are getting the results as the same vector I am receiving multiplied with some factor, then yes, x is the eigenvector. X is the eigenvector. And if we are not receiving the result like that, that means x will not be an eigenvector. Is that clear to you? So let's check example by example. Let's take the first example. So this is our matrix A, which is being multiplied with 1 0 0. So this is our matrix A, which is being multiplied with 1 0 0. So 2 0 0 0 2 0 0 0 3 is multiplied with 1 0 0. What you will receive? So 2 multiplied with 1, then 0 0 0. So sir, this will be 2. Then sir, this will also be 2. Oh, sorry. 2 multiplied with 1 will be 2, 0 0. Then 0 multiplied with 1, 0 0 and 0. And sir, 0 0 and 0. So this is what you are receiving. This is your result. When I saw this vector, what I thought? Let's take 2 common. So when I take 2 common, what I am getting? So what you saw here, this was your matrix A, right? And this was your vector x. What you are getting in the output, this is the final output. Again vector x multiplied with some constant value. So I am saying that there was a matrix A, I multiply with x1. Let's call this as x1. So what I am getting? I am getting the same vector x1 multiplied with some constant value, which is lambda 1. So here what is your lambda 1? Lambda 1 is 2. And what is your x1? X1 is nothing but 1 0 0. So 2 is a eigenvalue of matrix A. 2 is a eigenvalue of matrix A. 2 is a eigenvalue of matrix A. And x1 is a eigenvector corresponding to lambda 1. Is that clear too? Similarly, what was our next question? So yes, this is a eigenvector for sure. Next was 0 1 0. So 0 1 and 0. Do the multiplication. So 2 multiplied with 0, 0 multiplied with 0, 0 0. So 0 multiplied with 0 will be 0, 2 multiplied with 1 will be 2, and then 0 0. Then 0 sir, 0 here and 0 here. When I saw this vector carefully, I got to know that if I take 2 common, what I will be getting? This is what I will be getting. Again, you can sense that this is nothing but 2 into the same vector. Let's call this as x1 and let's call this as x2. Okay, so this is your x2. So it is the same thing. It is same, x2 is appearing here again, 2 into x2. Okay, so what is your eigenvalue? This is your eigenvalue, which is lambda 2 into x2. So x2 is the eigenvector and lambda 2 is the eigenvalue. Understandable? Say yes or no. So this is also one of the eigenvector. So this was the matrix A. I multiply this matrix A with 0 1 0. What I received? 0 2 0. Okay. Next I multiply with 5 0 0. 5 0 0. So what I will receive? So 5 into 2 10, and then rest everything would be 0. When I saw it carefully, what I got to know that I can take 5 common. Sorry, I can take yes, I can take 2 common. What I can take? I can take 2 common. So I will be getting 5 0 0. Now someone would say, sir, why don't you take 10 common? Sir, if you take 10 common, then this is something you will get. But this is the form that I don't want to make. No, I want to make this form. No, that A being multiplied with x3, A being multiplied with x3, it is giving me x3 again with some constant factor. So this is your x3. this is your x3, this is also your x3, and this is also your x3. So I want to make this kind of form, no? So that's why I'm taking 2 as a common, not 10 as a common, because if I take 10 as a common, then I will be getting 1 0 0. I will not be getting anything fruitful, right? So what I saw here is that what I am getting nothing but 2 into x3, or you can call it lambda 3 into x3. So shall I call it lambda 3? What is this? Lambda 1 equals to 2. What is this? This is also 2. What is this? This is also 2. So shall I write down lambda 2 here or lambda 1 only? What do you say? Let's write down lambda 1 only. Understandable? So till this point, what you have seen, with respect to one eigenvalue, with respect to eigenvalue 2, you have received this eigenvector, you have received this eigenvector, and you have received this eigenvector. With respect to eigenvalue 2, you are having 1, 2, 3 kind of eigenvectors till this point. Now, if you think closely, what you will understand that, sir, if 1 0 0 is an eigenvector, then for sure 5 0 0 will also be eigenvector. Because what I am saying is that if a is being multiplied with x1 and you are receiving some lambda 1 into x1. Now, if you multiply a with some 5x1, so what is 5? 5 is a constant value. 5 is a constant value. You can take 5 outward. And what is 5 into, what is a1 into x1? So a1 into, not a1, what is a into x1? 5 is a constant value that I took outward. A into x1 I am getting. So what is a into x1? A into x1 is nothing but lambda 1 into x1. Can I write down this as lambda 1 into 5x1? So what you saw here, that, sir, I multiplied my matrix A with 5x1. What I received? Lambda 1, 5x1. So this was your matrix. You multiplied this matrix with A. You are receiving your matrix again. Multiply with the constant value lambda 1. So it is pretty obvious, no, that if I am multiplying 1 0 0 with the matrix, I am getting 1 0 0 as the eigenvector, then it's a linear combination of x1, right? That could be 2x1, 3x1, minus x1, 3 by 2x1. That will surely be one of the eigenvector for sure. It is pretty obvious. The same kind of concept we studied in the null space as well. That if x1 and x2 are two of the eigenvalues, if x1 and x2 are two of the eigenvector, or I said if x1 and x2 belongs to the null space of A, then linear combination of x1 and x2 will surely belong to the null space of A. Is that clear to you or not? Do you remember that? If x1 is one of the eigenvector, x2 is one of the eigenvector, then their linear combination will also be one of the eigenvector for sure. So it is the linear combination only, no? It is simply x1 multiplied with 5. Okay. So from this particular question only we are going to make some conclusions. But as of now, whatever the conclusion that I am writing down, I hope that is clear to you. Understandable? Started with 1 0 0, we got the same result. It was multiplied with some factor 2. Started then 0 1 0, got the same result, multiplied with some factor 2. Took 5 0 0, got the same result, multiplied with some factor 2. So as of now we have got to know that x1, x2, x3, all these are eigenvectors with their corresponding eigenvalues. For all these 3 examples, the corresponding eigenvalue came out to be 2 only. Can you let me know what will be the eigenvalue of this particular vector, and will it be a eigenvector or not? Sir, if 0 1 0 is eigenvector, then this particular thing is nothing but 0 1 0 multiply with 5. 0 1 0 multiply with 5. So sir, if x2 is eigenvector, then sir, x2 multiply with some constant factor alpha. If x2 is eigenvector, then alpha into x2 will surely be one of the eigenvector for sure. There is no doubt about it, sir. So 0 5 0 will also be eigenvector, and sir, I can already comment that eigenvalue will come out to be 2 only. Why is that so? Let's check this out. So 0 5 0. So this will become 0. This is 10 and this is 0. Someone will say, let's take 10 common. No, I will take 5 common. I will take 2 common, not 5. Why is that so? Because I need to make 0 5 0 here. So what I am getting, some constant value which I am calling as lambda 1 only, multiplied our vector x4. So this is your eigenvector and this is your eigenvalue. This I am calling as x4. Again I am getting x4 here. Understandable? So it was pretty obvious that I already knew. What about 0 0 5? So sir, 1 0 0 you have taken, 0 1 0 you have taken. Sir, even if you take their linear combination, then also you will not get 0 0 5. So sir, this is a different eigenvector. 0 0 5 is a different eigenvector. Sir, even if you take their linear combination. What will be the linear combination of 1 0 0 and 0 1 0? Sir, multiply this with alpha and multiply this with beta and add both of them. So that will be alpha into 1 will be alpha, beta into 0 will be 0. Alpha into 0 will be 0, beta into 1 will be beta, and 0 0. So this will be the linear combination. So here this factor should be 0, but this factor is 5 here. So this is a different vector. So let's check that out if it is an eigenvector or not. And if it is an eigenvector, then eigenvalue will be different for sure. Why is that so? Eigenvalue might be different, not for sure. Eigenvalue might be different. Why eigenvalue might be different? Let's check that out. So 0 0 0 0 you are getting. So 0 0 0 again 0 you are getting, and 0 multiplied with 0, 0 multiplied with 0, here you are getting 50. So what common I will take? I will take common as 3, right? So if I am taking 3 as common, what I am getting here? So this was my x5, and in the output again I am receiving x5 only, but this eigenvalue is different this time. I am calling this as lambda 2. So what you are getting? Lambda 2 x5. So this is your eigenvector and this is your eigenvalue, which is different than the previous value, right? So yeah, that means yes sir, 0 0 5 is also one of the eigenvector, and the eigenvalue was 3. So with respect to the eigenvalue 3, the eigenvector was x5. Understandable? Let's check the next example. Sir, if 0 0 5 is one of the eigenvector, then I am pretty sure that sir 0 0 1 will also be eigenvector. Why is that so? Because it is simply multiply with 1 by 5. If you multiply this factor with 1 by 5, what you will be getting? 0 0 1. So if x5 is a eigenvector, then alpha into x5 will surely be one of the eigenvector for sure, right? So alpha into x5 will also be one of the eigenvector for sure. That means 0 0 1. So this will become 0, this will also become 0, and this will become 3, and this is 0 0 1. What common you are taking? 3. Again the same eigenvalue, and eigenvector is coming out to be x6. If I take this as x6, this is also x6, and this is my lambda 2. Okay, so what is the eigenvalue? Eigenvalue is also lambda 2. Okay, so eigenvalue is lambda 2. So with respect to eigenvalue 3, we are getting the eigenvectors 0 0 5 and 0 0 1. 0 0 3 will also be one of the eigenvector. Yes sir. 0 0 2 will also be one of the eigenvector. Yes sir. Right. Now what about the next example? Sir, 1 1 1. 1 1 1. Now someone would say that sir 1 0 0 was the eigenvector. Then sir 0 1 0 was the eigenvector, and sir 0 0 1 was also the eigenvector. Sir, if I take their linear combination, let's just say I simply add them, what you will be getting? 1 plus 0 will be 1, 0 plus 1 plus 0 will be 1, 0 plus 0 plus 1 will be 1. So sir, this is you will be getting. That means sir, their linear combination should also be one of the eigenvector for sure. So sir, I will say that this is also one of the eigenvector. Wrong. Why is that so? They were the eigenvector with respect to lambda 1, no? And this is the eigenvector with respect to lambda 2. What I mean to say is that a into x1 gave you lambda 1 into x1, right? And a into x5, and the other vector, let's call this as x2. So that also gave you lambda 1 into x2, right? A into x1, this was your x1, this I am calling as x1, and this I am calling as x2. Okay, this I am calling as x2. This was your x2. This is your x1, this is your x2, and this is your x6. So a into x1 gave you lambda 1 into x1, a into x2 gave you lambda 1 into x2, and a into x6 gave you lambda 2 into x6. Is that understandable to you? Right? Now let's do one thing. Let's add up equation 1 and 2. Let's add up equation 1 and 2. What I am doing, I am adding up equation 1 and 2. So what I will be getting? Sir, a into x1 plus x2. Then lambda 1 I can take common from here. Then x1 plus x2. This is what I will be getting. That means linear combination of x1 plus x2 it was. So matrix A multiply with this vector. Matrix A multiply this vector y is giving you lambda 1 y only. That means yes, y is the eigenvector. This is the eigenvector corresponding to eigenvalue lambda 1. Is that clear to you? Y is the eigenvector corresponding to eigenvalue lambda 1. It is absolutely fine. It is the linear combination of x1, x2. Both had the same eigenvalue. Both had same eigenvalue. Same eigenvalue. But what if I add equation 1 plus 2 plus 3? What I will be getting? If I add equation 1 plus 2 plus 3, I will be getting ax1 plus ax2 plus ax3. So what I can do is that I can take a as common. So here I will be getting a into x1 plus x2 plus x3. But on the other side, what I will be getting? So lambda 1 x1 plus lambda 1 x1 plus lambda 1 x2. So lambda 1 you can take common from here, plus lambda 2 x6. It is not 3, it is 6. What do you sense here? So let's call this as vector y, a into y. Am I getting some constant value y? Sir, y you cannot even take common. So lambda 1 was 2, this was 3. Right? So here y was being common, no? x1 plus x2 plus x3 I can take separate, and lambda 1 I could have taken separate. But can I take lambda 1 separate here? If both were same, then I could have taken it. But if both are different, then I cannot take it. So yes, linear combination of eigenvector will also be one of the eigenvector, but for the same eigenvalue, not for the different eigenvalues. Here it looks like that, sir, 1 0 0 is one of the eigenvector, 0 1 0 is one of the eigenvector, and sir 0 0 1 is also one of the eigenvector. So let's take their linear combination. We are getting the option G, which is x7. So sir, x7 will also be one of the eigenvector. But the question would be, what is the eigenvalue? So the question you will ask is that sir, what is the eigenvalue? With respect to x1, if I am having an eigenvalue lambda 1, with respect to x2 as well, I am having an eigenvalue lambda 1 only, and with respect to x6 as well, if I am having eigenvalue lambda 1, then for sure their linear combination will be an eigenvector. But sir, if they are having different eigenvalues, then it might not be an eigenvector. Is that understandable to you or not? So they need the same eigenvalues here, lambda 1 and lambda 1. Then only it would have been the eigenvector. Otherwise, it is not. Okay, and you can check as well 1 1 1. So sir, why you took these examples? These examples are not the examples which will be asked in the examination, but they will build up your concept. Okay, so these examples are taken to build up your concept, not to test your understanding. So here we are building up the concept, right? So when I multiply with 1 1 1, what I will be getting? Sir, 2 multiply with 0 will be 0, 2 multiply with 1 will be 2, then 0 and 0, then 0, 2 multiply with 1 will be 2, and then this will be 3. Can I take anything common? If I take 2 common, let's just say if I take 2 common, what I will be getting? 1 1 and 3 by 2, right? So if I call this as x7, right? So is this x7? No, this is not x7, right? That means not a eigenvector, not a eigenvector, not eigenvector. Is that understandable to you? So a into x7 cannot be written in some constant value x7, cannot be written in this form. That means it is not a eigenvector. I hope that is understandable to you. Okay, and the linear combination thing is also understandable to you. Why is that so? Because we got to know that they are having different eigenvalues, x1, x2 and x6. x1, x2 are having the same eigenvalues, but x6 is having different eigenvalues than a and b. So from this as well, we got to know that if they are having the different eigenvalues, then sir, this lambda 1 I am not able to take common. But if they were having the same eigenvalues, then their linear combination of eigenvectors was giving me another possible eigenvector. Is that understandable to you? What about 5 5 5? If x7 is not eigenvector, then its linear combination will also be not the eigenvector. 1 1 1 is not the eigenvector, then 5 5 5 will also not be the eigenvector. It is pretty obvious, no? Because 1 1 1 is not giving me 1 1 1 is not giving me the results, then 5 5 5 will also not give me the results. 5 into 2 10, 10 and then 15. What I will do? Let's take 2 as common. If I take 2 common, what I will be getting? 5 5, but here I will get 15 by 2. Again, not a eigenvector, not eigenvector. And what is the last one? Last one is also anything random, 5 5 4. Anything random I have taken 5 5 4. It is not the linear combination, nothing. Any random eigenvector, any random vector I have taken. So let's check that out. What I will be getting? 5 into 2, 10 sir. 2 into 5 sir, 10, and here you will be getting 12. what common I should take? Let's take 2 common. What you will be getting? 5, 5 and 6. So are they matching? No, they are not matching. What does that mean? Not eigenvector. So anything random cannot be eigenvector, right? Here, what all eigenvector you got? Sir, we got 1 0 0, 0 1 0, 5 0 0, 0 5 0, 0 0 5, 0 0 1. These 6 eigenvector we got. So can I write down what all eigenvectors I got? So corresponding to our eigenvalue lambda 2, corresponding to eigenvalue lambda equals to 2, these eigenvectors I got 1 0 0, 0 1 0, 5 0 0 0, 0 0 5. Can you let me know that I will have other eigenvectors as well? What that would be? Sir, that would be 0 3 0 as well. Why is that so? Because they are the linear combination. Along with that, sir, you will be having 2 0 0 as well. Why is that so? Because they are the linear combination. Along with that, sir, addition of these two as well. Addition of these two as well. Why is that so? Because of the linear combination. So what will be the addition of these two? 2 3 0. Sir, addition of these 3 as well, because linear combination. So 2 plus 2 4, 3 plus 3 6, 0. That will also be one of the eigenvector. So there will be infinite eigenvectors here. 1 0 0 is an eigenvector, 0 1 0 is an eigenvector, 5 0 0, 0 5 0, 0 3 0, 2 0 0, 2 3 0, 4 6 0. All these will be the eigenvectors. But in the complete linear algebra, I have said one thing, that if infinite eigenvectors are possible, or if infinite elements are possible, this is not a matter of concern for me. What is the matter of concern? Independent elements. So how many independent eigenvectors you are having? 2 independent eigenvectors you are having. Are they independent of each other? Yes, sir. Make a matrix. 1 0 0 0 1 0. Is it in row echelon form? Yes, sir. Row echelon form. What is the rank you are getting? 2. That means here I am having 2 independent rows. So yes, they are independent of each other. Rest everything is dependent. 5 0 0 is depending on 1 0 0. 0 5 0 is depending on 1 0 1 0. 0 3 0 depending on 0 1 0. 2 0 0 depending on 1 0 0. 2 3 0 depending on the linear combination of these two, and these are depending on these two guys. 4 6 0 depending on linear combination of these three, and these three are depending on these two guys. So everything is dependent. Only 2 independent eigenvectors we are having. 2 independent eigenvectors. So in the examination they will not ask you that with respect to eigenvalue 2 how many eigenvectors you are having. That will be the wrong question. You will say, sir, infinite eigenvectors I will have. With respect to lambda, with respect to eigenvalue 2, how many independent eigenvectors you are having? Sir, 2 independent eigenvectors I will have, rest all will be dependent. Sir, how will I find it out? That we will see. But as of now, you have understood one thing, that my matter of concern would be the independent eigenvectors. And with respect to all these eigenvectors, I was having the same eigenvalue. If I ask you one question, okay, x1 is a eigenvector corresponding to eigenvalue lambda 1. My question is, will 5x1 be a eigenvector? My question is, will 5x1 be a eigenvector? Yes, sir, it will be eigenvector. What will be its corresponding eigenvalue? 5 lambda 1. Wrong. These kind of simple question could be asked in the examination, and 7 out of 10 people will get it wrong. If x1 is a eigenvalue, sorry, if x1 is a eigenvector, then corresponding eigenvalue is lambda 1. If 5x1 is a eigenvector, yes, sir, it is a eigenvector. If it is a eigenvector, then what will be the corresponding eigenvalue? That will also be lambda 1 only, no? Here what I have written, you have seen here, that 1 0 0 was a eigenvector corresponding to eigenvalue lambda equals to 2. 5 0 0 was a eigenvector corresponding to eigenvalue lambda equals to 2 only. This was your x1, this was your x3. What is x3? x3 is nothing but 5x1. This is also 5x1. So with respect to 5x1, you are having an eigenvalue 2. With respect to x1, you are having eigenvalue 2 only. And it is pretty obvious. How will you think that, sir, a multiplied with x1 will give me lambda 1 into x1? Now, sir, a multiplied with 5x1, 5 is a common thing, sir. I will get 5 into lambda 1 into x2. Sorry, 5 into lambda 1 into x1. But my matrix is 5x1, sir. So if I need to make the same matrix, no? So lambda 1 will be outward, and here I need to make the same matrix, which will be 5 into x1 only. A into x1 is giving me lambda 1 into x1. Then I multiplied 5 here. So here also I will multiply with 5. But this is my matrix. So my matrix multiply with matrix A is giving me my matrix multiply with some factor. So what is that constant factor? That is lambda 1 only. So these kind of simple equation could be asked in the examination and you will be messing it up. Okay. So with respect to a matrix A, we are having an eigenvalue lambda 1. So and the corresponding eigenvector will be x1. So for the eigenvector 5x1, what will be my eigenvalue? People will click on 5 lambda 1. 8 out of 10 people will click on 5 lambda 1. But the answer would be lambda 1. You can do by this thing or you can remember the example. Okay, better will be this particular scenario, that in the examination you see this condition, based on that you write it down, then you see what is your vector, and based on that you see that what is my eigenvalue. Understandable? Yeah, so these kind of things in short somewhere you can write down. Next, eigenvector corresponding to lambda equals to 3. Sir, corresponding to lambda equals to 3, we got this eigenvector which was 0, 0, 5, 0, 0, 1. That's it. So here we saw, sir, 0, 0, 1 we saw. Then we saw, sir, 0, 0, 5. Can anyone let me know that 0, 0, 1 by 2 will also be the eigenvector or not? 0, 0, minus 2 will also be the eigenvector or not? And so on. But only one independent eigenvector we will have. Only one independent eigenvector we will have. Okay, just 1 second. Yeah, so what I was saying that here with respect to lambda 3 we will have only one independent eigenvector. So what I am saying, with respect to lambda equals to 2, we are having 2 independent eigenvectors. Right? And with respect to lambda equals to 3, we are having one independent eigenvector. Right? Is that clear? So total 3 independent eigenvectors we are getting for this matrix A. Right? And one more thing, are they independent of each other? Yes, it is pretty obvious that they are independent of each other, and this is also one of the independent eigenvectors, so they will be independent of each other. Basically, let's just say for this matrix A, I was getting x1 as a eigenvector, x2 as eigenvector, and x3 as eigenvectors. 3 independent eigenvectors I am getting. So they will be independent of each other, no? This guy and this guy is independent, and this guy is independent of both of these guys. What I am saying, this is independent of both of these people. Right? That means all 3 will be independent of each other. Pretty obvious, right? Are you able to understand this point? So all these points will again come up, but you need to keep on building up the concept, right? You need to keep on building up the concept. From this question, what we have understood, that yes, you can get different eigenvectors, but with respect to one eigenvalue, with respect to each eigenvalue, whatever the eigenvectors that you are getting, the linear combination of those eigenvectors will also be the new eigenvector for sure. But with respect to different eigenvalues, if you are getting 2 different eigenvectors, then it is not necessary that their linear combination will also be the eigenvector. Okay, so different eigenvalue is a different concept. Different eigenvalues you find no relation, but same eigenvalues, 2 different eigenvectors, then their linear combination will surely be one of the eigenvectors. Here it is proven as well. This particular portion is also very important. So when you revise, you will revise this portion as well. This is also very, very, very important. So here I will write down y is not a eigenvector, not eigenvector. Okay, so this portion is also very important. All these conclusions will also be written. No need to worry about it. This question is like your examination problem. I guess this is a gateway IQ only. So how will you find out how will you get this question correct in the examination hall? That matrix A is given, and which of them will be an eigenvector? This is the question they are asking. So what I will do is that, sir, in the examination quickly I will take this matrix, and then, sir, I will multiply with the first option 3, 3. So what I will be getting, sir, minus 12 plus 6 minus 6, and then, sir, 12 plus 6, 18. Okay, so, sir, here I can sense that no matter whatever I do, I will not be able to get 3 here. If I need to get 3 here, I need to take minus 2 common, but if I am taking minus 2 common, then here I will get minus 6. So it is not possible for me to get this kind of structure. So this is not an eigenvector. Then sir, again next option I will check minus 4 2. In quicker manner you will be able to check, right? It will not take much time. 4 3. So directly you will be doing the calculation in a quicker manner. So minus 16 plus 6, right? Minus 16 plus 6. So you will be getting minus 10 here. So and here you will be getting 16 plus 9, which will be 25. So pretty obvious, again you will not be able to get it, right? Again you will not be able to get 4 3, because if you need 4 here you would need 2.5, which will not give you the results, right? Next will be 2 minus 1. So what you will get, minus 8 and minus 2 minus 10, 12 and minus 3, 12 and minus 3 9, minus 8 minus 2 will be minus 10, 8 minus 3 will be 5. Okay, now I can see one thing, that sir, if I take minus 5 common here I will be getting 2 and here I will be getting minus 1. So yes, this is the eigenvalue and this is the eigenvector. So this option is correct. This also you can check, this will also not be correct. Okay, this also you can check, minus 4 2, 4 and 3, so minus 1 and 2. What you are getting, 4 plus 2 into 2 8, minus 4 plus 6 will give me 2. Okay, so no way, this is also not a eigenvector. Okay, so 2 into minus 1 will be eigenvector with the corresponding eigenvalue minus 5. And let me tell you one thing, in your competitive examination, no matter whichever the examination you are writing down, if there are 4 options A, B, C, D, A, B, C, D are the options, and you got to know that sir, I will have to check the options to get the answer of this question. I will have to check the options. There is a question having 4 options. You got to know that to check the answer of this question, to get the answer of this question, I will have to check the options. Without checking the option, I will not get the answer. So always first check option C, because A is in the beginning, D is in the beginning. What some people will do, that either they will start from A or they will start from D. So first check C, and most of the people will start from the beginning, no? So C will come at the third place, right? So first check C, then check B, and then any of A or D. Okay, so this should be the order. I always check from C. Even if you see the question paper of JEE, even if you see the question paper of GATE examination, I have seen one thing, that IIT professor set the option C only when you need to check the options. Okay, most of the times I have seen that option C would be the correct answer. So always check by option C, then go to B, and then any of A or D. Okay, so always in that order we should check. Here as well, I did not know that answer would be C. Okay, I did not know, but it came out to be C only. If I was there in the examination, I would have started from 2 minus 1 only. Okay, and I would have get the answer. If it was an MCQ, then without even checking all these options, I would have clicked on C. Right. So this is how we can save our time. Let's go to next concept, that how would I find out the eigenvalue of matrix A? That sir, here you solve these questions, you go to know that minus 5 is eigenvalue. Here you go to know that 2 is eigenvalue, 3 is eigenvalue. But sir, how will I find out these values? If matrix A is given, how will I find out the eigenvalues? Will I be thinking that 1 0 0 might be eigenvector? Then no, right? How will I find out the eigenvalues? And how will I find out the eigenvector as well? That also we will see. But let's first talk about the eigenvalues. So first we need to find out the eigenvalues. So how we will find it out? So let's assume that lambda is the eigenvalue corresponding to eigenvector x. Okay. So what does that mean? That if I multiply my vector x with A, so the result I will be getting is vector x only multiplied with some constant value lambda. Is that clear to you? So Ax will give me x only multiplies with some constant value lambda. So this is a constant value. Lambda is a scalar. Don't forget, it is not a matrix, it is a scalar. And A and x are the matrix. They are the matrix, right? Now what if, can I make somewhat like this, Ax minus lambda x equals to 0. Lambda x going there, right? If I take x common, what I am doing? I am taking x common. What I will write down here? Lambda. Let us say A is 2, 3, 4, 5, and lambda is a constant value, right? What I have done? Ax minus lambda x. Let's just say lambda is 3. So previously what I was doing, ax minus 3x. So a was a matrix, x was also a matrix, minus 3, x was also a matrix. So yes, it is absolutely fine to do like that. But when I take x common, what will come here? I will come, no? A minus lambda I will do, no? Because this is a matrix, this is also a matrix. This I need to make a matrix. Is that clear to you? X I am taking common, so here I would come, no? This is a square matrix. This also I need to make a square matrix, no? Lambda is a number. Lambda is a number. This is a scalar number or constant number. Scalar or a constant number. But from the matrix, I need to subtract the matrix only. So what will come here? Identity matrix would come. Lambda into I. So what does that mean? I am subtracting, like I is 1 0 0 1, lambda value was 3. So I am subtracting 3 0 3 3. You can take any random example where ax equals to lambda x, then you take a minus lambda I into x you do, and the result will be 0 only. Take any random example, you will be able to understand. If you are not able to satisfy that, sir, how this I came? This I came because this is a matrix and this is a constant value. I need to make it a matrix. So I will multiply with the identity matrix. Is that clear to you? Okay. So eventually what I have got is that I have got this condition that a minus lambda I into x is coming out to be 0. So if lambda is your eigenvalue corresponding, or you can say if lambda is one of the eigenvalue of matrix A and the corresponding eigenvector is x, then a minus lambda I multiply with x will be 0. I don't think it is very tough for you to understand. It is easy only. What you will remember this step, ax equals to lambda x, and the very next step you will be able to write down, that will be this particular step. How is that so? You will take lambda here, so a minus lambda I into x would be equals to 0. Now have we seen this kind of equation? Can I write down this equation as a minus lambda is a matrix only? A minus lambda I will also be a matrix. This will also be a matrix. So I am calling this as matrix C. Cx equals to 0. Can I write down this as Cx equals to 0? Yes, sir. Have you seen the solution of this equation? Cx equals to 0. Yes, sir. We have seen two kinds of solutions. One is unique solution, and other one is infinite solution. What is the condition of unique solution? Condition of unique solution is that it should be a full rank matrix, right? It should be a full rank matrix, or you can say that, or you can say, let's say A is a n cross n matrix, okay? A is a n cross n matrix. So C will also be n cross n, C will also be n cross n, right? Because A minus lambda I will also be n cross n, so C will also be n cross n matrix. So what was the condition? That rank of A minus lambda I, or rank of C should be equals to full rank. And here rank of C, which is A minus lambda I, should be less than n. It should not be full rank. If it is full rank, then what would be the solution vector? What would be vector x? Sir, vector x has to be the null vector. And if it is not a full rank, then vector x could be anything. Here elements would come, and these elements would belong to R. Here some elements would come, here some elements would come. These elements would be, it is not necessary that they will be real, they could be complex as well. I don't care about it, whether they are real or complex, I don't care about it. But in this case, only one vector is possible, which is 0 0 0. Do you remember the last lecture of null space? In null space also I said that 0 0 0 will never be my matter of concern. Why is that so? Take any random matrix, no? Here I would have taken this matrix. Someone would say that, sir, I need to get ax equals to lambda x. Then one intelligent guy would come that no matter whatever the matrix you take, if I multiply this matrix with 0 0 0, eventually I will end up getting 0 0 0 only. And here the constant value lambda equals to 1 I can take. So what will happen? Someone would come and say that x is my eigenvector corresponding to eigenvalue lambda equals to 1. Someone would say I will take 2 here. 2 multiplied with 0 0 0 will also be 0. So my eigenvalue will be 2 as well. Someone would say I will take 3 by 2. Someone would say I will take minus 1. So with respect to all possible eigenvalues, 0 0 0 will be the eigenvector, no, and no matter whatever the matrix is there. I don't even know what is my matrix A. So any random matrix you take, multiply that with 0 0 0, eventually you are going to get 0 0 0 only. And here you can multiply any constant factor. So in that manner you will have infinite eigenvalues and only one eigenvector, which is 0 0 0. So 0 0 0 is not considered as an eigenvector. If you remember the definition, what we have written, non-zero vector x. So 0 0 0 is not an eigenvector. Even in the null space also, I said that 0, 0, 0 we will ignore. We will not care about 0, 0, 0. So here you can clearly see that non-zero eigenvector we want. So if we are studying the concept of eigenvector, we are only talking about the non-zero eigenvectors. What we are talking about? We are only talking about non-zero eigenvectors. Is that clear to you or not? Understandable? Okay, so 0, 0, 0 will never be my matter of concern. What does that mean? This condition I don't want. Which condition? This condition I don't want. So what I will say? Not desired. This is not the desired condition. But which is the desired condition? This is the desired condition. And if you want this condition, what is the scenario? That means it should not be a full rank matrix. And if it is not a full rank matrix, can I say one thing about it? That determinant of matrix C, which is A minus lambda I, determinant of a matrix C, which is A minus lambda I, that should be equals to 0. There you go. So matrix A would be given. You will find out matrix A minus lambda I. You will calculate its determinant and put that equals to 0. You will get the value of lambda from here. And that will be your eigenvalues. Is that understandable to you or not? Do you remember this thing? I hope you remember it. Like at least 50 times we have written that if it is not a full rank matrix, then its determinant would be 0. It will be irreversible. All those things we have written, right? So if it is not a full rank matrix, A minus lambda is not a full rank matrix. That means it will have some nullity. What is the meaning of nullity? That means it will have a all 0 row. If it is having a all 0 row, what does that mean? Its determinant will be 0. So if it is not a full rank matrix, then its determinant would be 0. So in the examination, if they are asking how to find out the eigenvalues, what you will do? Matrix A would be given. You will find out the matrix A minus lambda I. Then you will calculate its determinant and you will equate it to 0. You will get the values of lambda. That's it. We will solve example and it will be clear to you. So let's take this example. In this example, a lot of things are asked. What is the things they are asking? That first they are asking characteristics equation, characteristic polynomial. Sir, I don't even know. Second question they are asking eigenvalues. Yes, that I know, sir. I will try to find it out. Next question what they are asking? Arithmetic multiplicity, geometric multiplicity. I don't know. Sir, eigenvectors they are asking, that also I can find out. Then nullity, a lot of things I don't know, right? So with respect to this question we will learn. Okay, what is the meaning of algebraic multiplicity or not algebraic multiplicity? It is arithmetic multiplicity. Okay, this name is algebraic also you can say, but arithmetic multiplicity. Then geometric multiplicity, what is the meaning of that? What is the meaning of characteristic polynomial? What is the meaning of characteristic equation? All those things we will learn, and how we can comment on the nullity of A minus lambda I, that we need to see. So what is our matrix A? This is our matrix A. What we need to find out? Let's take question B. Sir, we need to find out the eigenvalues. Eigenvalues we need to find out. So I told you one thing, for finding out the eigenvalues, what you do? Calculate A minus lambda I, calculate this matrix, take its determinant and equate it to 0. Okay, so this is our matrix A, which is this one, which is 2, 0, 0, 0, 2, 0 and 0, 0, 5. What I will calculate? A minus lambda I will calculate. A minus lambda I. What I will calculate? I will calculate a matrix C, which is A minus lambda I. So matrix A is given minus lambda I, 1, 0, 0, 0, 1, 0 and 0, 0, 1. So can this lambda go inside? Lambda multiplied with 1 will be lambda only. Here also this is lambda, here also this is lambda. This is also lambda, this is also lambda. So what you will be getting? A minus lambda I, what that will be? 2 minus lambda, then 0 minus 0, then 0 minus 0, then 0, 2 minus lambda, and that is 0, then 0, 0 and then 5 minus lambda. This is your A minus lambda I. From now onwards, if some matrix I have given A, B, C, D, E, F, G, H, I, and I ask you to calculate A minus lambda I, will you follow this process? No. You know that, sir, identity matrix will have only these elements as lambda. Rest all will be 0, 0, 0 only. And then I need to subtract. So what I will do? Directly I will subtract minus lambda, and minus lambda. I will get my A minus lambda I. Is that clear to you? Because I know that, sir, lambda I will have only these elements as lambda, 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 lambda. No. Rest all element will be 0. So A minus lambda, E minus lambda, I minus lambda. That's it. So 2 minus lambda, 2 minus lambda, 5 minus lambda. There you go. Okay. So I don't need to follow all these processes that this is how I am subtracting. Directly I will be able to write down this particular matrix. Now what I need to do, I need to equate the determinant equals to 0. Okay. Five minus lambda. Can you calculate its determinant? Yes, sir. I will calculate with respect to. I will calculate with respect to first row. So what I am getting? 2 minus lambda multiply with 2 minus lambda multiply with 5 minus lambda coming out to be 0. Or I can write down in a better sense. I want to write down lambda minus 2. I am taking minus common. Okay. Lambda minus 2 and lambda minus 5. So 3 minus common I have taken. So this is the negative sign I will be getting. That is equated to 0. Understandable? Okay. Now this particular, can you solve these equations? Yes, I can solve this equation, but this particular thing, this thing which is on the left hand side, is it a function of lambda? Is it a function of lambda? Yes, sir. What is the function of lambda you are getting? Lambda minus 2 and lambda minus 5, right? This is the function of lambda you are getting. And what is the equation that you are getting? The equation that we are getting is p lambda equals to 0. This is the equation we are getting, and this is the function we are getting, right? So this is known as characteristics polynomial. What it is known as? Characteristics polynomial. And what this is known as? This is known as characteristics equation. Characteristics equation. So eventually this is your characteristics equation. This is your characteristics equation, and this is your characteristics polynomial. Polynomial means it is a function, not equated to 0, it is a function, and this is your characteristics equation. Is that clear to you? I hope it is understandable. Very straightforward thing. So this is my characteristic equation, this is my characteristic polynomial, and if I solve this equation, what is my characteristic equation? So your characteristics equation is lambda minus 2 multiply with lambda minus 2 multiply with lambda minus 5 equated to 0. If I solve this equation, the value of lambda I am getting is, value of lambda, here you will get 2, here also again you will get 2, and here also again you will get 5. So these are the eigenvalues I am getting. Someone would say that, sir, eigenvalue is repeated. Yes, eigenvalue is repeated. So eigenvalues that you are getting is 2 to 5. What eigenvalues you are getting? Sir, eigenvalues that I am getting is 2 to 5. So 2 to 5 are the eigenvalues that you are getting. Okay. So eigenvalue 2 is repeated twice. So eigenvalue 2 repeated twice, and eigenvalue 5 only came once. So this is known as algebraic or arithmetic multiplicity. This is known as arithmetic multiplicity. So if I ask you, what is the arithmetic multiplicity of eigenvalue lambda equals to 2? What is that? So you will write down, sir, arithmetic multiplicity of lambda equals to 2. Arithmetic multiplicity of lambda equals to 2 is nothing but 2. It is repeated twice. Okay. And what is the arithmetic multiplicity of eigenvalue lambda equals to 5? That is 1. So how many times eigenvalue is repeated, that is known as arithmetic multiplicity. Okay, how many times the eigenvalue is repeated, what that is known as? That is known as arithmetic multiplicity. So arithmetic multiplicity of lambda equals to 2 is 2, and arithmetic multiplicity of lambda equals to 5 is 1. Understandable? So we have seen the meaning of arithmetic multiplicity, we have seen the meaning of characteristics polynomial and characteristic equation. What is this? Isn't it characteristic equation only? Sir, when you solve this particular side, then only you got this equation, no? Are you able to understand this point? When I solve this side, determinant of a minus lambda I, when I solve determinant of a minus lambda I, then I got this particular equation, no? That means it is nothing but characteristic equation only. This is your characteristic equation. Characteristics equation. And what do you mean by characteristics polynomial? This particular side is characteristics polynomial. Which side? This side is characteristics polynomial. Okay. So what is your characteristics polynomial? This is your characteristics polynomial. Characteristics polynomial. Okay, so in textbook this would be written that characteristic polynomial is determinant of a minus lambda I. Characteristic equation is determinant of a minus lambda I equals to 0. That is pretty understandable to you. Another thing, if eigenvalues are mentioned, okay, if eigenvalues are mentioned, which are 2, 2 and 5, can I write down the characteristics equation? These eigenvalues are mentioned. Let's call these eigenvalues as lambda 1, lambda 2 and lambda 3, where value of lambda 1 is 2, value of lambda 2 is 2 and value of lambda 3 is 5. Okay, someone would say they are same. Yes, they are same. If eigenvalues are mentioned, lambda 1, lambda 2 and lambda 3, can I write down the characteristic equation? Characteristics equation. Can I write down this equation? Yes sir, you will be able to write down the equation. It will be lambda minus 2 or lambda minus lambda 1, lambda minus 2, lambda minus lambda 2, lambda minus 5, which is lambda minus lambda 3, that would be equated to 0. So if I know the eigenvalues, I will be able to write down the characteristic equation as well, and from here I would get to know that this will be my characteristics polynomial as well. Okay. Although characteristic equation will be the matter of concern, characteristic polynomial will not be a matter of concern, but still we will be able to write it down. Okay, well and good. So this much we have seen, right? So all these points you need to understand. What was the order of this matrix? 3 cross 3. If you solve this characteristic equation, what will be the maximum power of lambda you will get? So lambda minus lambda 1 will be multiplied with lambda minus lambda 2 multiplied with lambda minus lambda 3. So lambda will be multiplied with lambda will be multiplied with lambda. So maximum power of lambda here, maximum power of lambda will be equals to 3 only, or you can call it n if the order was n cross n. If the order was n cross n, the maximum power of lambda would have been n. What does that mean? That means there could be 3 roots of this equation, whatever the maximum power is there. Let's just say I give you one equation, ax square plus bx plus c equals to 0. So how many roots it will have? 2 roots it will have, alpha and beta. Now it might be possible that sir both of the roots are same. It might be possible, no, that both of the roots are same, but maximum 2 roots it can have. So if there is a matrix of order n cross n, so what is the maximum number of different eigenvalues it can have? If there is a matrix of order n cross n, then it can have maximum n different eigenvalue. Is that understandable to you or not? Ax square plus bx plus c will have 2 different roots. Similarly, if I am having 3 cross 3 matrix, then I can have maximum 3 different eigenvalues, because its characteristic equation will be of the form lambda minus lambda 1 multiplied with lambda minus lambda 2 multiplied with lambda minus lambda 3 equals to 0. So for a matrix of n cross n, the maximum number of eigenvalues, maximum number of different eigenvalues will be equals to n. Say yes or no? Or you can say it will surely have n eigenvalues, but some eigenvalues might be same. That here it is having 2, 2, 5. It is having 3 eigenvalues which are 2, 2, 5, but they are same. But surely it will have 3 eigenvalues. 2 of them are same. 2 and 2 are same. Is that understandable to you? So if there is a matrix of order n cross n, then it will surely have n eigenvalues. Okay, it will surely have n eigenvalues, but some of them might be same. Understandable? So these things we have seen. Eigenvalues we have find out, eigenvalues we have find out, and we have find out the characteristic equation, we have find out the characteristics polynomial, and all these things. Next, what we need to find out? We need to find out the eigenvectors, and then we will understand the meaning of this geometric multiplicity as well. Okay, so let's find out the eigenvectors. Our next target is finding out eigenvectors. So what equation we are having? The equation we are having is Ax equals to lambda x. Okay, and we got to know that in lambda we are having these elements 2 and 3, sorry 2 and 5, sorry guys, 2 and 5. Eigenvalues are 2 and 5. So here we are having 2 and 5. When we write down the vectors, no, sorry, when we write down the set, we don't write down the repeated value. In set, repeated values will not come. So this set should be written as 2 and 5. So we are having two different eigenvalues, which is 2 and 5. So let's find out the eigenvector corresponding to lambda equals to 2. This is what we are doing. So let's just say my eigenvector is x only. My eigenvector is x. So what it will give me? Ax will give me 2x, right? Because eigenvalue is 2. So when a is multiplied with x, it should give me 2x. What is my a? Sir, a is your 3 cross 3 matrix, which is given as 2 2 0, 0 2 0, and 0 0 5. Now this will be a vector x. In this vector x, x1 element would be there, x2 element would be there, x3 element would be there. That should give you 2 x1 element, x2 element, and x3 element. Say yes or no? This will be the scenario. This vector x would be this kind of vector, no? x1 element would be there, x2 element would be there, x3 element would be there. Understandable? Ax should give you 2x. From here, can I write down the equation? 2 into x1 multiplied with 0, 0. So 2x1 is coming out to be 2x1 only. 0, 2x2 multiply 2x2 is coming out to be 2x2 only. And 5x3 is coming out to be 5 into x3 is coming out to be 2x3 only. Isn't it obvious that x1 will always be equal to x1? Always. What does that mean? It is a free variable. Say yes or no? 2x1 is coming out to be equal to 2x1. 2x1 is coming out to be equal to 2x1. So x1 minus x1 will be equal to 0. 2 and 2 is getting cancelled out. x1 minus 0 equals to 0. It is always true, no? So it is a free variable. What about the condition here? x2 is coming out to be equal to x2. It is also always possible. So what does that mean? It is also a free variable. Right? And what about this guy? Is it always true? 5x3 equals to 2x3. No, let's just say x3 is 1. So 5 equals to 2. Is it true? No. What does that mean? I need to solve it. 5x3 equals to 2x3. So this x3, 2x3 comes here. So what I will get? 5x3 minus 2x3 equals to 0. So 3x3 equals to 0. So from here, x3 equals to 0 we are getting. So value of x3 is 0. Value of x1 and x2 are free. So what will be your solution vector? Let's call x equals to x1 as c1 and x equals to x2 as c2. Okay, they are the free variables. They are the free variables that we are having. What does that mean? That means our eigenvector is coming out to be somewhat like this. Eigenvector is coming out to be somewhat like this. x1, x2 and x3. This is c1, this is c2 and this is 0. c1, and this is c2. I hope you remember this particular part. In null space we understood this part, that how I will write down this. So c1, c2, c3. So this will be 1, 0 and 0, because c1 multiply with 1 will give you c1, c1 multiply with 0 will give you 0, c1 multiply with 0 will give you 0. Now what do you need here? Here you need c1. So c1 multiply with 1 will be c1, c2 multiply with 0 will be 0. So c1 plus 0 will be c1 only. Here what you need? Here you need c2. So c1 multiply with 0 will be 0, c2 multiply with 1 will be c2. So this is how I can write down C2 and this value is 0. That means in both of the vectors you would know that x3 will be fixed, but we are having these two different vectors, which is 1 0 0 and 0 1 0. Two independent eigenvectors we will have. So with respect to lambda equals to 2, the eigenvectors are, let's call this eigenvector as v1 and this eigenvector as v2. So eigenvectors would be v1, v2, alpha v1, beta v2 and their linear combination. But only two independent eigenvectors we will have. Two independent eigenvectors we will have. Right? Two independent eigenvectors we will have. Is that clear to you? So with respect to lambda equals to 2, two independent eigenvectors we will have. Now what about with respect to lambda equals to 5? So find out that this is the process of finding the eigenvectors, okay? But what if, sir, in the examination we will do this much process, it will take a lot of time. So for that we took this question, no? In the examination these kind of question can come when it comes to eigenvector. So you check by the options. Basically, if someone would say that, sir, I need to find out the eigenvector, so what I will do, first I will find out the eigenvalue, then he will do this process, a minus lambda equals to 0, he will get the value of lambda, and with respect to each eigenvalue he will find out the eigenvectors, and then he will match the option, which is not desirable, right? Because I know the concept of eigenvector, no? Eigenvector means simply matrix multiply with that vector will give me that vector only multiply with some factor. So if I know the concept, then I will check the options, right? But here, just for the theory purpose, who knows, in the examination it might be used. So just for the theory purpose we are doing it, and we will make some conclusion here, okay? As of now you can see that with respect to lambda equals to 2 we are having two independent eigenvectors, and you know that lambda was repeated, 2 was repeated, so some conclusion we are going to make, okay? Have some patience. So what do you mean by geometric multiplicity? If someone would ask what is the, okay, we will write down geometric multiplicity later on, but let's first find out the eigenvector corresponding to lambda equals to 5, and I will have to add the pages as well. So I will add some page. So what we are finding out, eigenvector corresponding to lambda equals to 5. Eigenvector corresponding to lambda equals to 5. This is what I am supposed to find out. Understandable? So let's find it out. What I will do, sir, a multiply with the vector x will give me 5x. Sir, matrix A is given 2 0 0 0 2 0 and 0 0 5. Multiply with vector x, which will be x1, x2, x3. It should give me 5x, which should be 5x1, x2 and x3. Can I solve this equation? Sir, here also you took x1, x2, x3. Ideally I should have taken x4, x5, x6. But I hope you are not getting confused. This is a separate part. This is also a separate part. All I need to find out is this vector. That is my matter of concern, right? So 2x1, 2x2, 5x3. So first I will get 2x1. From this equation I will get 2x1 should be equals to 5x1. This is the equation I am getting. Then I am getting 2x2 should be equals to 5x2. 2x2 should be equals to 5x2. And then the equation that I am getting is 5x3 should be equals to 5x3. 5x3 should be equals to 5x3. This is always true, sir. Always. This is always true. That 5x3 will be equals to 5x3. Take any value of x3. x3 equals to 2, 10 will be equals to 10. x3 equals to 5, 25 would be equals to 25. So this is, sir, always true. But sir, these are not always true, no? That I have to solve. So here I will get minus 3x1 equals to 0. Here I will get minus 3x2 equals to 0. So if I solve the equation, this is always true, which is free variable, right? But here I am getting, sir, x1 equals to 0, x2 equals to 0 and x3 equals to some free variable I am taking, which is c3. So what is the solution vector that I am getting? Solution vector x1, x2, x3 that I am getting is, sir, 0 0, which are fixed, but some constant value C3. That could be written as C3 0 0 1. So this is the eigenvector we are getting. This is the eigenvector we are getting, right? So eigenvector corresponding to lambda equals to 5, right? What is the eigenvector you are getting? So eigenvector corresponding to lambda equals to 5, how we made it? Corresponding to lambda equals to 5, we were getting was, let's call this as V3. So V3, some 2V3 and some gamma V3 you will get. But there is only one independent eigenvector. Here there is only one independent eigenvector. One independent eigenvector. Understandable? Is that clear to you? Now let's understand the meaning of a geometric multiplicity. Geometric multiplicity. What is the meaning of a geometric multiplicity, which is GM? The meaning of geometric multiplicity is that number of independent eigenvectors. Number of independent eigenvectors corresponding to each eigenvalue. Each eigenvalue. That is the meaning of a geometric multiplicity. If I ask you, what is the geometric multiplicity of eigenvalue 2? What you will say? 2. Why is that so? Because we are having two independent eigenvectors. What we are having? We are having two independent eigenvectors. With respect to lambda equals to 2. With respect to lambda equals to 2, we are having two independent eigenvectors. Two independent eigenvectors. Eigenvectors, which are V1 and V2. And what is geometric multiplicity of lambda equals to 5? That is 1. Why is that so? Because we are having one independent eigenvector, which is V3. Is that clear to you? So V1 and V2 are independent, and V3 is also one independent eigenvector we are having, right? One more thing, V1, V2, V3 will be independent of each other as well. Look, about V1 and V2, I have already said that V1 and V2 are independent of each other. That's why I am saying two independent eigenvectors are there. But the doubt would be that, sir, let's just say I was having a matrix A. Okay. Through this matrix A, I am getting these kind of eigenvalues. Lambda 1, again lambda 1, then lambda 2 and lambda 3. These kind of eigenvalues I am getting. With respect to these eigenvalues, I am getting two independent eigenvectors. Two linearly independent eigenvectors I am getting. And here, with respect to lambda 2, I will get one independent eigenvector. And here also I will get one independent eigenvector. Let's call this here we were getting two independent eigenvectors V1, V2. Here I am getting independent eigenvector V3. Here I am getting independent eigenvector V4. First of all, one thing is for sure that if there is an eigenvalue, which is repeated only once, this eigenvalue has been repeated only once, then there could be only one independent eigenvectors. There could be only one independent eigenvector. If it is repeated only once, then there could be only one independent eigenvectors. Let's just say, sir, one eigenvalue is repeated twice. So how many independent eigenvectors it will have? Sir, it may have one as well, or it may have two as well. But maximum it can have two. One eigenvalue is repeated twice. lambda 1, lambda 2. It is repeated twice. So maximum it can have 2 independent eigenvectors. It cannot have more than 2 eigenvectors. Here this was repeated twice. How many eigenvectors it had? 2. It might be possible that it will have only one independent eigenvectors. It might be possible. We will see the example. Okay, don't worry. We will see the example. There it will have only one independent eigenvector. But maximum it can have 2. This is repeated only once. Lambda 2 is coming only once. So it will have one independent eigenvector. It is coming once, it will have one independent eigenvector. It is coming twice, it may have 2 or more than 2. And whatever the eigenvectors you are getting, they will be all independent of each other. What does that mean? That means these eigenvectors that I will get, this eigenvector, this eigenvector, this eigenvector, this eigenvector, all will be independent of each other. V1, V2, V3, V4, all will be independent of each other. All are independent of each other. Independent of each other. Is that understandable to you or not? Okay. Well and good. Now let's talk about the nullity. So till this point we have understood the meaning of geometric multiplicity as well. We have understood the meaning of algebraic multiplicity as well. So let's write down the values of geometric and algebraic multiplicity. So what all values you were getting? यार ये अच्छा लग रहा है ऐसे, या फिर let's do this thing. Yes. So what is the algebraic multiplicity we were getting? What is the meaning of algebraic multiplicity of lambda equals to 2? What does that mean? That means how many times lambda equals to 2 has been repeated? Twice. And what was the algebraic multiplicity of lambda equals to 5? How many times lambda equals to 5 has been repeated? That is 1. Right? How many times lambda equals to 5 has been repeated? That means how many times you have got the eigenvalue lambda equals to 5? That is 1. And what is the geometric multiplicity? Here in the last what I have written here. I hope I did not write down 5. Okay, algebraic multiplicity I explained. Where I explained algebraic multiplicity. Yeah, 1 only. Okay. So in written sometimes I can write down 5 here, but I hope you understand. How many times lambda equals to 5 has been repeated? Only once, no? Right? Or one more thing before this I will write down that the eigenvalues that we were having was 2, 2, 5. They were 2, 2, 5. And with respect to 2, 2, we got eigenvalues which were V1 and V2. And with respect to 5, we got eigenvalue which is eigenvector which is V3. With respect to 2, 2, we got 2 independent eigenvectors which were V1 and V2. That means what was the geometric multiplicity of lambda equals to 2? That was 2. And what was the geometric multiplicity of lambda equals to 5? That was 1. Because with respect to lambda equals to 5, we got only one independent eigenvector, and with respect to lambda equals to 2, we got 2 independent eigenvector. So I hope the meaning of algebraic multiplicity and geometric multiplicity is clear to you. AM, GM I will call them. Understandable? Let's understand the meaning of nullity of A minus lambda I. What we are understanding? Nullity of A minus lambda I. So we are having this equation for eigenvectors. We are having this equation that Ax equals to lambda x. From here we are getting the equation A minus lambda I into x equals to 0. And one thing also I know that if I am considering the eigenvector, I can take only one condition, that rank of A minus lambda I should be less than n. Or can I say nullity of A minus lambda I would be greater than or equals to 1, or I can say greater than 0. Is that understandable to you? Nullity of A minus lambda I would be greater than 0. Can I say so? Quickly think about it. This is your 3 cross 3 matrix. If it is having rank less than n, let us say rank is 2. So 1, 2, 3, 0, 2, 4. Rank is 2. That means this has to be all 0. So what is the nullity? Nullity would be the number of columns minus the rank. So what is the nullity? Nullity is 1. So nullity has to be greater than 0. Now what does nullity represent? Nullity represents the number of free variables. Number of free variables. And this number of free variables, what does it represent? Number of independent vectors. In the last lecture of null space we saw number of free variables. Here how many number of free variables were there? Only one free variable was there. So how many independent vector I got? 1. How many number of free variables were there here? How many number of free variables were there? those two are the free variables. Two free variables. Two free variables. Two free variables. If I am having two free variables, then what I got? I got two independent eigenvectors. The same thing we saw with respect to null space as well. Do you remember dimension of null space? So we calculated the nullity, and what we were saying, nullity of A would represent the number of free variables. The number of free variables would represent the number of independent solution. The number of independent solution would represent the number of independent vectors in the null space of A. Similarly, here nullity of A minus lambda I would represent the number of free variables, and it will represent the number of independent vectors, or you can say number of independent eigenvectors with respect to the eigenvalue lambda. What it will represent? Number of independent eigenvectors number of independent eigenvectors with respect to eigenvalue lambda. Let's understand by the example. This was the concept. If you are following the concept right from the beginning, from the system of homogeneous equation, then you will be able to understand this concept. Otherwise, you can take the example. What you can take? Let lambda equals to 2. Let lambda equals to 2. So what will be my matrix? A minus 2i, right? A minus lambda I, A minus lambda I. So what I am supposed to find out? I am supposed to find out the nullity of A minus lambda I. So can I find out A minus lambda I? Yes, sir. What was my A? A was 2 0 0 0 2 0 0 0 5. What was A? 2 0 0 0 2 0 0 0 5 minus lambda 2i 2 0 0 0 2 0 0 0 2. What you will get? 2 minus 2 will be 0, 0 minus 0 will be 0, 0 minus 0 will be 0, 0 minus 0 will be 0, 2 minus 2 will be 0, 0 minus 0 will be 0, 0 minus 0 will be 0, 0 minus 0 will be 0, and 5 minus 2 will be 3. You can interchange the rows and column. This is the matrix that you are getting. Can you comment on the nullity? Nullity of A minus 2i. What you are getting? That you are getting as 2. This is the nullity you are getting. What you can comment? It will have two independent eigenvectors. Can you comment on the nullity of A minus 5i? Yes, sir. A minus 5i. A was, sir, 2 0 0 0 2 0 0 0 5 minus 5i 5 0 0 0 5 0 0 0 5. What you will end up getting? Sir, I will end up getting 2 minus 5 will be minus 3 0 0, 0 minus 0 will be 0, 2 minus 5 will be minus 3 0, and 0 0 and 0. There you go. Is it in the row echelon form? Absolutely, sir. It is in the row echelon form only. What is the nullity you are getting? The nullity of A minus 5i I am getting as 1. What does that mean? It will have one independent vector. One independent eigenvector. So what does nullity of A minus lambda 1i, A minus lambda 1i represents? What does this represent? Lambda 1, basically here lambda 1 is 2, here lambda 1 is 5. So A minus lambda I would represent the number of independent eigenvectors, the number of independent eigenvectors with respect to eigenvalue lambda equals to lambda 1. There you go. Are you mugging it up? Are you mugging it up? Are you just seeing some example and then you are making the conclusion? No. With the concept we are making the conclusion. If you feel like that, sir, we need to see the example as well, then here is the example. So from this particular question, what all things you have understood? You have understood the meaning of characteristics polynomial. What is characteristics polynomial? Determinant of A minus lambda I. That is your characteristics polynomial. Have you understood the meaning of characteristics equation? Yes, sir. Determinant of A minus lambda I equated to 0 is the characteristics equation. Have you understood the meaning of finding out the eigenvalues of A? Yes, sir. How will you find out the eigenvalues of A? Determinant of A minus lambda I should be equated to 0. Then you will be able to find out the eigenvalues of A. Sir, I equated that to 0. I was able to find out the eigenvalues of A, which were 2 to 5. With respect to eigenvalues, can you comment on the arithmetic multiplicity? Yes, sir. Arithmetic multiplicity simply means how many times the eigenvalue has repeated. Lambda equals to 2 has been repeated twice, lambda equals to 5 has been repeated once. So that is known as the arithmetic multiplicity. Then can I find out the eigenvectors? Yes sir, I can find out the eigenvectors. Along with that, I go to know one thing: if there is a matrix of n cross n, then maximum number of eigenvalues I can have, maximum number of different eigenvalues I can have is n. There could be some same eigenvalues, there could be some different eigenvalues as well. So, but maximum number of different eigenvalues I can have is n. Then can I find out the eigenvector? Yes sir, I know the equation ax equals to lambda x. I need to get lambda equals to 2. So that I put. Simply I will solve the equation, I will get the eigenvector. In this case, I was getting two free variables, two independent eigenvectors I was having. Here I was getting one free variable, one independent eigenvector I was having. Then I understood the meaning of geometric multiplicity. What is the meaning of geometric multiplicity? The number of independent eigenvectors you are getting with respect to a particular eigenvalue. So with respect to eigenvalue 2, I was getting two independent eigenvector, and with respect to eigenvalue 5, I was getting one independent eigenvector. Right? That I understood. Along with that, I understood one more thing. Let's just say there is a, can you let me know what will be the order of matrix A? That will be 4 cross 4. Why is that so? Because I am having 4 eigenvalues. So if I am having 4 eigenvalues, okay, lambda 1, lambda 1, lambda 2, lambda 2, I am saying that from my side it is given that lambda 1 and lambda 1, these are giving me two independent eigenvectors, which is v1 and v2, and this is giving me one independent eigenvector, and this is also giving me one independent eigenvector, right? So if we are getting v1, v2, v3, v4, they will be surely independent of each other. So all these eigenvectors will be independent of each other. But here this is not the surety, okay? This is not the surety that for sure you will get one independent eigenvector. This is not sure. Not one, I should say two. With respect to the repeated eigenvalue, you will get two independent eigenvectors. That is not sure. But these are not repeated, no? So one eigenvector you will get here. Here also one eigenvector you will get. But here it is coming twice. So you may get 2 or you may get 1. If one eigenvalue is repeated 4 times, this is repeated 4 times. So maximum how many independent eigenvectors I can have? So maximum independent eigenvectors I can have 4, or I can have 3 as well, or I can have 2 as well, or minimum I will have 1. So with respect to lambda 1, I can have 1 independent eigenvector as well, or 2, or 3, or 4. I cannot have 5 independent eigenvector. Is that understandable to you? I hope it is understandable. It is absolutely clear to you, right? So here, if lambda 1 is repeated twice, then you can have 2 independent eigenvectors, and that is the case here. Here we are having geometric multiplicity of 2 and arithmetic multiplicity of 2 as well. Understandable? Then we would show that how will I find out what will be the geometric multiplicity? So basically what this is representing, nullity of a minus lambda I. Basically what is nullity of a minus lambda I is representing? Nullity of a minus lambda 1 I. What it is representing? It is representing nothing but geometric multiplicity of lambda 1. That how many independent vectors it will have. If I need to find out the with respect to lambda equals to 2, how many independent eigenvectors you are having. So what I would do? I would calculate the nullity of a minus 2i. So nullity of a minus 2i came out to be 2. So with respect to lambda equals to 2, I am having 2 independent eigenvectors. And why is that so? Because nullity would represent the number of free variables. Number of free variables means number of independent solution. Number of independent solution means number of independent eigenvectors. So these many independent eigenvectors I will have. So nullity of a minus lambda I represents the geometric multiplicity of lambda, or you can say how many times or how many eigenvectors, independent eigenvectors you are having with respect to a eigenvalue lambda equals to lambda 1. Is that understandable to you or not? So this is a complete revision question which is telling you most of the things about eigenvalues and eigenvector. I hope it is completely understandable to you. Again we will solve one more problem. There we will understand more concepts. What do we need to find out? Eigenvalues you find out. Okay. So make the matrix, calculate a minus lambda. It will be a tough calculation. Okay. It will be a tough calculation. This will be a tough calculation. In the examination, this kind of tough calculation might not be asked, but who knows, it may be asked as well. So calculate it on your own. Sir, calculating the determinant of 3 cross 3 is fine. But sir, 4 cross 4, it will be a bit tough, sir. Yes, it will be a tough task, but you need to do it on your own. Try it on your own. And then what equation you will get? This equation you will get, which I have already written down. Okay. So you try doing it on your own and find out the eigenvalues. Once you have found out the eigenvalues, can you find out the algebraic multiplicity and geometric multiplicity? Yes, sir. That also we can find out. And then you will be able to comment on the relation of AM and GM. Okay. You will be able to comment on the relation of algebraic multiplicity and geometric multiplicity. When you solve it, you will understand the relation. When you solve it, you will understand the relation. Okay. And then you will tell me the total number of independent eigenvectors. And after that, you will calculate the trace and determinant of this matrix A, and you will comment something. comment on the relation to the eigenvalues of A. So 4 questions you can solve, and then you can calculate the trace and determinant. What will be the relation, that we will see. That you leave up to me. I will take a break and then I will come back, but I ask you to solve this question on your own. Will you do it for me? Will you do it for yourself? Yes sir, you will. We will do it. We will do it everything on our own. We will find out the eigenvalues as well. Then we can comment on the algebraic multiplicity from here. Then for finding out the geometric multiplicity, what I need to do? I need to calculate the nullity, sir. Then I will calculate the nullity. Then I will see what is the relation I am getting. And then I will be able to tell the total number of independent vectors as well. And then I will calculate the determinant and trace, and I will comment on the relation. As of now, if you don't know the relation, I will tell you the relation. Understandable? So do it on your own and I will come back. Okay. Yeah, welcome back. So did you solve this question? So our matrix A was given. We are supposed to find out the eigenvalues, right? So what we need to do, if we need to find out the eigenvalues, what we will do is that A minus lambda I, we will equate that to 0. And when we solve this particular equation, what kind of equation we will be getting? We will be getting this kind of equation. Lambda minus lambda 1 multiply with lambda minus lambda 2 multiply with lambda minus lambda 3 multiply with lambda minus lambda 4. Why is that so? Because sir, this is the characteristic equation. From this equation only I will get 4 kind of roots. Why 4 kind of roots? Because this is a 4 cross 4 matrix. That means I can get 4 eigenvalues. Now these eigenvalues might be same, they might be different. I don't know that. So this kind of equation I will be getting, and after solving this equation, sir, I will be able to get to know my eigenvalues. Right? So A matrix is given minus lambda I. So from here I will subtract lambda, 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 and then I will calculate the determinant, and then I will equate it to 0. So when I equated, this is the equation I was getting, and from here I go to know that I am getting the eigenvalues at 2, 2, because lambda minus 2 square is there, no? That means eigenvalue 2 is repeated twice, 3 is repeated once, and 5 is repeated once only. What does that mean? That means, sir, your algebraic multiplicity of lambda equals to 2 is 2. Your algebraic multiplicity of eigenvalue 3 is 1, and your algebraic multiplicity of eigenvalue 5 is also 1. Understandable? So this we have seen. Now what we need to find out? We need to find out the eigenvectors, or we need to comment on the geometric multiplicity. We are not supposed to find out the eigenvectors, we need to comment on the geometric multiplicity. So let's comment on the geometric multiplicity of lambda equals to 5. Can you let me know what will be the geometric multiplicity of lambda equals to 5? Or first let's talk about the geometric multiplicity of lambda equals to 3. Sir, that will be equals to the nullity of A minus lambda I, which is A minus 3i. Can you let me know the answer without even doing the calculation? Sir, it will be 1 only. Why is that so? Because this is repeated only once. The eigenvalue is coming only one time. That means it will have maximum 1 independent eigenvector and minimum as well 1 independent eigenvector. Right? I hope you understand that if lambda equals to 3 is coming, this is one of the eigenvalues. So with respect to one eigenvalue, you will have 1 independent eigenvector. Or we can check. Let's calculate the nullity of A minus 3i. What is your matrix A? And from that you need to subtract 3. So you need to check the nullity. So let's check the nullity. Okay, it will not be difficult. We can simply see 4 minus 2, 1, 0. So I need to subtract 3 here. So 1 minus 2, 1, 0. 1 minus 2, 1, 0. Then 2 minus 3, 1, 0. Then 0 here, again 0. Then here I need to subtract 3 and this will become 1. Right? And then I need to subtract 3. So 1 minus 1, 0, 2. This is your A minus 3i I have calculated. A minus 3i. What is the meaning of A minus 3i? That means all the diagonal element will be subtracted from 3. So this will become 1, this will become minus 3, this will become 0, and this will become 2. 1, minus 3, 0, 2. Rest all the elements are same. Minus 2, 1, 0, 2, 1, 0, 0, 0, 1, and then 1 minus 1, 0. Yes. So this is your A minus 3i. Now what I need to do? I need to find out the nullity. So let's try finding out the nullity. So I need to find out the rank. I need to get the row echelon form. But if I check something, can I get the answer in a quicker manner, or I will have to follow the complete procedure? I will have to follow the complete procedure only. So how do we find out the row echelon form? So in row 2, I need to do row 2 minus 2r1. Right? And in row 3, I need to, in row 4, I need to do row 4 minus row 1. then I will get the matrix and I will be able to comment on the rank. Okay, this process you should not be watching, you should be doing it on your own, because we have studied rank way before, right? So you should be able to do all these things on your own. Twice I am subtracting here, so 0, twice I am subtracting here, 1, minus 1, 0. Then this is, I am not doing anything about it, and then here I am directly subtracting, so this will become 0, this will become 1, this will become minus 1, and this will become 2, right? So more operation I can do, what I can do is that I can add up row 2, row 4 and row 2, right? Basically what I am going to do now is that from row 4 I will subtract row 2. Okay, so what matrix I will be getting? In a quicker manner I am writing down. So matrix that I will be getting is 1, minus 2, 1, 0. From row 4 I am subtracting something, no? So let's keep this as it is, and this will be 0, 0, 0, 0, 1 only, and the last one would be 0, 0, because it is being subtracted, 0, and this will become 2. And next what you are going to do? Next you are going to do in row 4, next this came here. Okay, next what you are going to do is that from row 4 you are going to subtract row twice of row 3, twice of row 3. So what you will be able to see? You will be able to see one thing, that sir, it is 1, 2, minus 1, 2, 1, 0. Nothing is happening with the first 3 rows. So first 3 rows will be as it is, sir. They will be as it is. And now, sir, twice of this is subtracted. So directly I can sense that, sir, it is a row echelon form. Rank of A minus 3i is coming out to be 3. That's why nullity of A minus 3i is coming out to be number of columns 4 minus 3, that is equals to 1. So nullity is 1. What does that mean? What does that mean? That means my geometric multiplicity is also 1. My geometric multiplicity, that means number of independent eigenvectors with respect to lambda equals to 3, I will have only 1. And here as well, I don't need to calculate. I know that geometric multiplicity with respect to lambda equals to 5 will also be 1 only. Is that understandable to you or not? Absolutely, it is understandable. But now I need to comment on lambda equals to 2. I need to find out that geometric multiplicity of lambda equals to 2. What does that mean? I need to find out how many independent vectors I am having with respect to lambda equals to 2. That means I need to calculate the nullity of A minus 2i. So then I will able to understand how many independent vectors I am having with respect to eigenvalue 2. Okay. So how many independent vectors I am having? So what I will do is that I will simply copy this one. Right. So here I subtracted 3, but I am supposed to subtract 2. So what I need to do is that in the diagonal element I need to add 1. So this will become 2, this will become minus 2, this will become 1, and this will become 3. Basically what I am doing is that I am subtracting 2 from the diagonal element. So here you will get 2, here you will get minus 2, here you will get 1, and here you will get 3. 2, minus 2, 1, 3. And rest all the elements are same. Minus 2, 1, 0, 2, 1, 0. Rest everything would be same. Now what I need to do? I need to calculate the nullity. Directly you can see that these two rows are the same. Right? And then I need to get the row echelon form. So let's get the row echelon form. So how will you get the row echelon form? In R4 what you do? R4 is being subtracted with half of R1. Right? And R2 what you do? R2 minus R1 you do. So what you are going to get? 2 minus 2, 1, 0. Right? So here 0, 0, 0, 0, 0, 0, 1, 1, and here half of that you are subtracting. So this will become 0, 0 only, this will be 0 only, and this will be 3. So will it be in the row echelon form? You just interchange both of them. Yes, they will be in the row echelon form, and this is the all 0 row. What is the rank you are getting? So rank of A minus 2i is coming out to be nothing but 3. So what will be the nullity of A minus 2i? So that will come out to be rank minus, number of columns minus the rank, that is coming out to be 1. So nullity of A minus 2i is coming out to be 1. What does that mean? Geometric multiplicity of lambda equals to 2 is coming out to be 1 only. What do you understand from here? I will have only one independent eigenvector. Only one independent eigenvector. Independent eigenvector. Is that understandable to you or not? So geometric multiplicity of lambda equals to 2. Although it is being repeated twice, but only one independent eigenvector you will have. Can you find out that eigenvector? Yes, sir. Simply multiply x1, x2, x3 equals to x1, x2, x3, x4 equals to 0, and then you will get the eigenvector. You will get to know that 3x4 will come out to be 0. That means x4 will be equals to 0. From here x1, x2 value also you will be able to get. Are you able to understand what I am saying? What I mean to say is that if I am supposed to find out the eigenvector, what I will do, a minus 2i multiply with vector x, that should be equated to 0. What is a minus 2i? This is a minus 2i. But I told you, after doing the transformation, after applying the transformations, whatever the matrix that you are getting, that also you can write down here, and then you can multiply with your variables x1, x2, x3 and x4, and when you solve those variables you will get the answer. Basically 2 minus 2 1 0, here 0 0 0 0 0 0 1 1 and 0 0 0 3. So from here you can get to know that 3x4 is coming out to be 0, and x3 plus x4 is coming out to be 0. Then this is 0 equals to 0 only, and in the first equation you are getting 2x1 minus x2 plus x3 equals to 0. You will be able to understand all those things if you have followed the previous lectures, right? So from here what you will be able to get, x4 is coming out to be 0. From here x3 is also coming out to be 0. Now if x3 is coming out to be 0, then equation from here you are getting is 2x1 equals to x2. So one of the free variable could be there. Let's just say if x2 is, or let's just say if x1 is c, then what will be x2? X2 will be 2c. So what is the solution vector you are getting? The solution vector that we are getting is x1, x2, x3, x4. So the solution vector that we are getting is, this is c, this is 2c, and this is 0 0. So c you take common, 1 2 0 0. Only one free variable we are getting, or you can say one independent solution we are getting, or you can say one independent eigenvector we are getting, which is 1 2 0 0. So this is the independent eigenvector we are getting. So what is your geometric multiplicity here? So let's copy this particular thing. Let's copy this particular thing here, and we can comment on the geometric multiplicity as well. That geometric multiplicity is coming out to be, geometric multiplicity is coming out to be 1. Here what is the geometric multiplicity? 1. Here also 1. From here you can comment that algebraic multiplicity will always be greater than geometric multiplicity, and it is pretty obvious as well. Why is that so? Let's just say I am having a matrix 7 cross 7 matrix, okay, and its eigenvalues are lambda 1, lambda 2, lambda 3, lambda 3, lambda 4, lambda 4 and lambda 4. Okay, so 7 eigenvalues it should have. So 3 to 5 to 7 eigenvalue it should have. So now it will have one independent eigenvector, one eigenvector. This will also have one independent eigenvector, one independent eigenvector. These are repeated twice. It may have one or two independent eigenvectors. So what is the algebraic multiplicity of lambda 1? Algebraic multiplicity of lambda 1, that is 1. And what will be the geometric multiplicity? Here for sure you can say that, sir, one independent eigenvector I will have. What is the algebraic multiplicity of lambda 2? That is also 1. And for sure I can say that I will have one independent eigenvector. But here what is the algebraic multiplicity of lambda 3? Sir, that is 2. Lambda 3 is repeated twice. Now how many independent eigenvectors you will have? Sir, either I will have 1 or 2. I cannot comment. And what about these guys? Algebraic multiplicity, that means how many times lambda 4 has been repeated? That is repeated thrice. But how many independent vectors you will have? So sir, I can have independent vectors either 1 or 2 or 3. Is that understandable to you? Either 1 or 2 or 3. Is that clear? Here also 1, 2 or 3. And whatever the independent vectors you are having, they will be also independent of each other. Let's just say here I am having v1 vector, here I am having v2 vector, and considering here only one independent vector is there and here two independent vectors are there, or only one independent vector is there? This is what I am considering. So 4 independent vectors I am getting, v1, v2, v3, v4. So they will also be independent of each other. Is that clear to you? These guys will also be independent of each other. So this is the relation we are getting, that arithmetic multiplicity will always be greater than the geometric multiplicity, am greater than gm. Is that understandable to you or not? So what all questions we have answered? First one was find the eigenvalues of a. Then for each eigenvalue find out the algebraic multiplicity. Comment on the relation. Find out the total linearly independent vectors. How many total linearly independent vectors we are having? So sir, for matrix A, we have find out that we are having the eigenvalues 2, 2, 3 and 5. So basically it was a 4 cross 4 matrix. So we were having 4 eigenvalues. With respect to this guy, I was having only one independent eigenvectors. Here also only one independent eigenvector, and here also one independent eigenvector. Sir, they are independent of each other. They are independent of each other. So total 3 independent eigenvectors. Total 3 independent eigenvectors. Is that true or not? So total 3 independent eigenvectors we are having. So this is answered. Find out the trace and determinant of A. What is the trace of A? Trace. Trace means addition of all the main diagonal elements. So that will come out to be 12, right? 4 plus 3, 7, 7 plus 5, 12. And what is the determinant of A? Can you find out the determinant? Yes, sir. You do the, what I will do my expansion with respect to second row, or I can do the my expansion with respect to, sorry, this is your second column. I can do the expansion with respect to third column as well, so third row as well, or I can do the expansion with respect to fourth column, because here there are 2 0 element, here also 2 0 element, here also 2 0 element. So how you will do it? You can do the expansion with respect to fourth column. Okay, so plus minus, this will be minus, this will be plus, then minus, and then plus. So directly I will go to this 1. So 1, then that is gone. So what you are left with? 4 minus 2, 1, 2 0 1, 1 minus 1, 1 minus 1 0. So plus minus plus minus plus minus. So minus sign would come up here. Then again next plus 5. So I will block the row and column with respect to 5. Block the row and column with respect to 5. What I will be left with? 4 minus 2, 1, 2 0 1, 0 0 3. So what I will be getting here? This is 3. And what will be the determinant of this one? That will be 3 multiplied with 4 into 0 will be 0, 0 minus 4, that will be 4. So this will become 12. So this determinant was 12, right? So 5 into 12, here I was getting 5 into 12. So this was 60. And what is the determinant of this one? So let's find out the determinant here. So minus 1 is already there. I need to find out the determinant of this matrix. So what I would do, I would plus minus plus, I would do it with respect to last row. So last row minus 2, then 1. You should do it all on your own, right? I am not supposed to do the calculations and all, but again this is a recorded video, so I don't know if you are able to calculate the determinant or not, but at least you should be able to calculate the determinant. Till this point, if you are studying in this lecture eigenvalue, eigenvector, which is nearly the end of linear algebra, then you should be able to calculate the determinant. What you will do? Pick up what we were doing it with respect to fourth column, right? Fourth column, right? Fourth column. So this was your fourth column. Then I did it with respect to 0, it will be 0 only, then 0 0. And you remember the concept of cofactor, right? Plus minus plus minus plus minus in the alternative order. So this will be minus 1. Then block the row and column. This is the matrix that you are getting. You need to find out the determinant of this matrix, that is coming out to be 0 only. Okay, the determinant is coming out to be 0. So here it was 60, so it is coming out to be 60. Okay, the determinant is coming out to be 60. So this is the condition we are getting. We have calculated the determinant as well, and we have calculated the trace as well. So determinant is coming out to be 60. You should be able to do it on your own. Understandable? So this is the scenario. What all are your eigenvalues? Sir, eigenvalues are 2, 3, 5, right? 2, 3, 5. If you write down that, sir, my eigenvalues are 2, 3, 5, this is wrong. Your eigenvalues are 2, 2, 3, 5. What are your eigenvalues? Sir, eigenvalues are 2, 2, 3, 5. If I add up all the eigenvalues, let's just say this is lambda 1, this is lambda 2, this is lambda 3 and lambda 4. If I add up all the eigenvalues, what it will come out to be? Lambda 1 plus lambda 2 plus lambda 3 plus lambda 4. So 2 plus 2, 4, 4 plus 3, 7, 7 plus 5, 12. It is coming out to be trace of A. And if I multiply all the eigenvalues, even if it is repeated, then also you need to take in action. 2 into 2, 4, 4 into 3, 12, 12 into 5, 60, which is determinant of A. So what do you understand? Addition of eigenvalues. Addition of eigenvalues will represent the trace of matrix A, and the multiplication of eigenvalues will represent the determinant. Will you be able to remember this? Yes, sir. So whatever that we have studied, conclusion of everything we are going to write down. Yeah, but one more page I am having. After that we will write down the conclusion. We will solve this question, and after that we will write down the conclusion. But from this particular question, what is the conclusion that we are making? We have understood the meaning of algebraic multiplicity. We have understood the meaning of geometric multiplicity. The nullity of A minus lambda I will represent the geometric multiplicity of lambda, and arithmetic multiplicity will always be greater than the geometric multiplicity. It is pretty obvious. Now this particular matrix was having 4 eigenvalues. 2 of them were same. 2 of them were same, right? 2 of them were same. They were having one independent eigenvector. This was also having one independent eigenvector, and this was also having one independent eigenvector. So total 3 independent eigenvectors they were having. Although it is a 4 cross 4 matrix, but it is having total 3 independent eigenvectors. Maximum it can have 4 independent eigenvalues, 4 different eigenvalues and 4 independent eigenvectors. But here, with respect to the repeated eigenvalue, I was having only one independent eigenvector. But in the previous example, with respect to the repeated eigenvalue, I was having 2 independent eigenvectors. So it was repeated twice. It was repeated twice, and 2 independent eigenvectors I was getting, but here I am getting only one independent eigenvector, which is pretty obvious because nullity may be lesser, right? But with respect to the repeated eigenvalue, you can never get 3 independent eigenvectors. No. With respect to 2 different eigenvalues, with respect to 2 different eigenvalues, I can only get maximum 2 independent eigenvector. With respect to 2 different eigenvalues, I can maximum get only 2 independent eigenvectors, which is pretty obvious and very easy to understand. Right? So all these things we have seen, and then we got to know that trace of A, trace of matrix A is simply the addition of all the eigenvalues. Trace of matrix A, which is 12, which is simply the addition of all the eigenvalues, lambda 1 plus lambda 2 plus lambda 3 plus lambda 4, and the determinant of matrix A. Determinant of matrix A is simply the multiplication of all the eigenvalues. Understandable? So this also you will remember. Let's see this question. You need to think of this question and need to give me the answer. Okay, we are not commenting on the nullity of A minus lambda I. We are commenting on the nullity of A. So which of the following statements are true? Matrix A is there, which is of order n cross n. Can you let me know what will be the meaning of nullity of A minus lambda I? That means it will comment on the geometric multiplicity of what? Eigenvalue, geometric multiplicity of eigenvalue, or let's call it lambda 1. So it will comment on the geometric multiplicity of eigenvalue lambda equals to lambda 1. Understandable? Now they are talking about the nullity of A. If I want to make this function as nullity of A, what I need to do? Let lambda 1 equals to 0 is one of the eigenvalue of eigenvalues of A. If it is one of the eigenvalues of A, then what will happen? Nullity of, here you will put lambda 1 equals to 0. What you will get? Nullity of A equals to geometric multiplicity of lambda equals to 0. There you go. What it is representing? What nullity of A is representing? Nullity of A is simply representing the number of independent eigenvectors corresponding to lambda equals to 0. So what nullity of A is representing? Nullity of A is representing the number of eigenvectors corresponding to lambda equals to 0. So if nullity of A is greater than or equals to 1, that means if nullity of A, or you can say geometric multiplicity of A is greater than or equals to 1. So this is what they are saying, that geometric multiplicity of lambda equals to 0 is greater than or equals to 1. One thing you already know, that algebraic multiplicity is already greater than the geometric multiplicity, right? And this value is already greater than equals to 1. This value is already greater than equals to 1. What does that mean? That means algebraic multiplicity will also be greater than or equals to 1. What does that mean? The number of times lambda equals to 0 you are getting as an eigenvalue, that is more than 1 or equals to 1. That means for sure at least once you will be getting the 0 eigenvalue. And it is pretty obvious. No, you are saying that here I am having more than one independent eigenvector with respect to eigenvalue lambda equals to 0. So someone is saying that with respect to lambda equals to 0, I am having more than one eigenvector. That means 0 would have come at least once. No, let's just say there is a matrix whose eigenvalues are 0, 0, 0 and 4. These are the eigenvalues. So with respect to 0, 0, 0, you will have at least one eigenvector. At least one eigenvector you will have. So if I am saying that I am having one eigenvector with respect to 0, 0, 0, that means 0 is surely eigenvalue. No. Is it always necessary that such 0 will be eigenvalue? No, it is not always necessary. Why is that so? If you take a matrix A and multiply with the vector x, then you need to get vector x only. It should be multiplied with a constant factor. It could be 3, it could be 2, it could be 1, it could be 0 as well. If it is 0, then 0 into 0 will be 0. So x will be eigenvector corresponding to lambda equals to 0 only if ax equals to 0. And ax equals to 0 is always not possible. Ax equals to 0 is always not possible. Can you say that, sir, I will take a random matrix A and I will take a random column vector A and I will multiply both of them and I will always get 0? No. There has to be some specific x, no? There has to be some specific A. Always it is not possible. Understandable? Always it is possible if x equals to 0. But we are talking about the non-zero vectors, right? So for non-zero vector x, always it is not possible that you will get ax equals to 0, right? What is the condition? Condition is that rank of A should be less than equals to n. So it should not be a full rank matrix. If it is not a full rank matrix, that means its nullity would be greater than equals to 1. So this is what first option is saying. So all the things you can relate. We have studied about null space as well. We have studied about ax equals to 0 as well. We have studied about ax equals to b as well. You are able to relate everything. What we are saying is that if nullity is greater than or equals to 1, nullity is greater than or equals to 1. What does that mean, sir? That means nullity of A minus lambda is greater than equals to 1. Lambda is 0. So it is representing the number of independent vectors with respect to eigenvalue lambda equals to 0. You are having greater than 1 or equals to 1. What does that mean? That means one eigenvalue I will have which is lambda equals to 0 for sure. Is that clear to you? Nullity of A represents the number of linearly independent eigenvectors corresponding to eigenvalue lambda equals to 0. Absolutely correct. Nullity of A represents the algebraic multiplicity of eigenvalue 0, means the number of times 0 has repeated 0 has appeared as an eigenvalue of A. This is wrong. Why is that so? What I have said is that let's just say nullity of A has come out to be 0. So the nullity of A has come out to be 2. What does that mean? That means geometric multiplicity of lambda equals to 0 is 2. Say yes or no? Right? Nullity of A means nullity of A could be written as nullity of A minus lambda I, A minus 0 I, that is equals to 2. So nullity of A is equals to 2. That means geometric multiplicity of lambda equals to 0 is 2. And one thing you know that AM is greater than or equals to GM. That means algebraic multiplicity of lambda equals to 2 is greater than equals to 2. So what you can write down? From this statement, what you can write down? The number of times eigenvalue 0 has appeared is 2. Is that statement correct? No. What will be the correct statement? Is at least 2. Is at least 2. Say yes or no? That means eigenvalue 0 would have been repeated at least twice. So here the number of times 0 has appeared. No. The number of times, minimum number of times 0 has appeared. This would have been the correct statement. No. So it is not representing the arithmetic multiplicity. It is representing the geometric multiplicity. And if geometric multiplicity is 2, that means arithmetic multiplicity would be greater than or equals to 2. If I am saying that with respect to this matrix, I am having some particular eigenvalues Okay, I am having some particular eigenvalues, and here with respect to a particular eigenvalue, I am having two independent eigenvectors. Two independent eigenvectors. Then you will say that if you are having two independent eigenvectors, that means at least twice that eigenvalue would have been repeated. At least twice that eigenvalue would have been repeated. Even if it is repeated 3 times, then also you can have two independent eigenvectors and one value could be different. So this is the similar thing we have written, that if it is having two independent eigenvectors, then it might be possible that the value is repeated thrice, right? So it is not representing the algebraic multiplicity, it is telling the minimum number of times that a value has been repeated, minimum number of time. Okay, and if 0 is an eigenvalue, then determinant of A will surely be equal to 0. Why is that so? Let's just say there is a matrix A which is having a eigenvalues of lambda 1, lambda 2, lambda 3 and 0, right? So what will be the determinant of A? So determinant of A will be simply lambda 1 multiplication of all the eigenvalues, lambda 1, lambda 2, lambda 3 multiply with 0, that will be equal to 0 only. And it is pretty obvious, if 0 is one of the eigenvalues, then nullity of A would surely be greater than or equal to 1, and if nullity is greater than or equal to 1, then determinant will also be equal to 0. So from here also you can tell. So all the points are interrelated. The only thing is, if you don't want to think much, what you will understand, that what is the meaning of geometric multiplicity? Geometric multiplicity means, sir, simply nullity of A minus lambda I. What does it represent? The number of independent eigenvectors with respect to lambda equals to lambda 1. If I am saying that nullity of A means, sir, lambda 1 equals to 0 I need to put. That means it will represent the number of independent eigenvectors with respect to the eigenvalue lambda equals to 0. So if I am saying that nullity of A is greater than or equals to 1, that means at least one independent eigenvector I am having with respect to lambda 1 equals to 0. So if I am having at least one independent eigenvector, that means at least once the value 0 has been repeated as an eigenvalue. So 0 would have come as an eigenvalue at least one time. It could be 2 times, it could be 3 times, it could be 4 times, whatever it is, I don't know. But if I am having one independent eigenvector, that means at least once the value has come. So this has been written here. Nullity A represents the number of linearly independent eigenvectors with respect to eigenvalue lambda equals to 0. It represents the number of times the value has been repeated? Absolutely not. It represents the minimum number of times the value has been repeated. If nullity of A is 1, that means minimum one eigenvalue I will get 0. If nullity of A is 2, then minimum 2 eigenvalues I will get 0. It could be 3 as well, it could be 4 as well, that I don't know. But minimum 2 I will get. If nullity of A is 4, then minimum 4 0 eigenvalues I will get. If nullity of A is 7, then minimum 7 0 eigenvalues I will get. Is that clear to you? And if 0 is one of the eigenvalues, then determinant would be 0 only. Say yes or no. So very, very deep points, but in a very easy manner we have understood everything. Only thing you need to remember is this one. That's it. If you remember this particular thing, your job is done. If you remember this particular thing, your job is done. And what is the actual meaning of geometric multiplicity? That also you need to know. What is the meaning of geometric multiplicity? The number of independent eigenvectors that you are having with respect to one eigenvalue. Well and good. I hope it is understandable to you. That's it. Okay. So this is these are the properties that we are going to write down. Here we have written all the properties that we will see later on. But one more small property is there. So this is a diagonal and a triangular matrices. This is a diagonal matrix, right? This is a upper triangular matrix, and this is a lower triangular matrix. This we have understood in the basics, right? What is the trace here? A plus B plus C. And what is the determinant? A into B plus C. What is the trace here? A plus B plus C. And what is the determinant? A, B, C. What is the trace here? A plus B plus C. And what is the determinant? A, B, C only. Can you find out its eigenvalue? What you will do for finding out the eigenvalues? Sir, minus lambda, minus lambda, minus lambda, and then I will calculate the determinant and equate it to 0. So when I calculate the determinant equated to 0, the eigenvalues will come out to be ABC only. And it is pretty obvious as well. Eigenvalues will come out to be ABC only. And it is pretty obvious as well because addition of eigenvalues will represent the trace and multiplication of eigenvalues will represent the determinant. Is that understandable to you? If I find out the eigenvalues here, A minus lambda, A minus lambda, A minus lambda I will be doing, and do the expansion with respect to first column. Do the expansion with respect to first column. Then what you will get? A minus lambda multiply with B minus lambda multiply with C minus lambda. Okay, you will get this answer only. Then you will understand that, sir, eigenvalues are ABC only, and here as well eigenvalues are ABC only. And it is pretty obvious as well. Why is that so? Because addition of eigenvalues will represent the trace and multiplication of eigenvalues will represent the determinant. Understandable? So a plus b plus c is the trace, a into b into c is the determinant. So what I am saying is that these are the diagonal elements. No, these are the diagonal elements. These are the diagonal elements. So for an upper triangular matrix and for a lower triangular matrix, the eigenvalues are their diagonal elements only. In a triangular or diagonal matrix, the eigenvalues are simply the elements of the main diagonal. Elements of the main diagonal. And this example we have seen previously as well. The very first example that we picked up, no? What were the eigenvalues? When you solved it, eigenvalue. This is a diagonal matrix. Eigenvalues were 2, 2, 5. 2, 2, 5. Main diagonal element. Same goes for lower triangular as well, and same goes for upper triangular as well. Is that clear to you? Not a very tough thing to remember. Absolutely very easy thing to remember. Okay, let's write down all the properties. What is the basic definition? This is the basic definition. Ax equals to lambda x. X is the eigenvector of A. Lambda is the corresponding eigenvalue. What do you mean by diagonal? What do you mean by the eigenvalues of a diagonal and trigonal matrix? They will be equal to the diagonal element, right? Then characteristic equation. What is the meaning of characteristic polynomial? Determinant of a minus lambda I. This is known as determinant of a minus lambda I. Okay. And what is the meaning of characteristic equation? Determinant of a minus lambda I equated to 0. That is the meaning of characteristics equation, and roots of this equation will represent the eigenvalues. This is also the basic thing. What is the meaning of trace and determinant? So trace of matrix A will be equal to the addition of all the eigenvalues. Let's just say this is our matrix A, which is having lambda 1, lambda 2. Matrix A of n cross n, it is having n eigenvalues. So addition of lambda 1 plus lambda 2 plus dot 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 lambda n will represent the trace of A, and similarly multiplication of lambda 1, lambda 2, lambda 3 dot 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 lambda n will represent the determinant. Okay. Nullity and eigenvalue 0. If nullity is greater than or equals to 1, then 0 will be eigenvalue for sure, and nullity of A would represent the number of independent eigenvectors with respect to lambda equals to 0. This we have proven, and we have given roughly around 20 to 25 minutes of discussion here, right? If one of the eigenvalue is lambda equals to 0, then nullity of A would be greater than or equals to 0, or you can say the number of independent eigenvectors with respect to lambda equals to 0 will be at least 1. Okay, and nullity of A would represent the number of independent eigenvectors of lambda equals to 0, or you can call it, what you can call it, geometric multiplicity of lambda equals to 0. And you would also know one thing, that algebraic multiplicity of lambda equals to 0 would be greater than the geometric multiplicity here. That means at least 1, at least 0 will be one of the eigenvalue for sure. This is what it will say. Geometric multiplicity. What is the meaning of geometric multiplicity? That means nullity of A minus lambda I. What it represents? It represents the number of linearly independent eigenvectors corresponding to lambda. Right? What is the meaning of algebraic multiplicity? Number of time eigenvalue has been repeated, or it has appeared as a root of characteristic equation. Right? What is the relation? That arithmetic multiplicity would be greater than, this is written as arithmetic multiplicity would be greater than or equals to geometric multiplicity, or it would be greater than or equals to 1. It is pretty obvious, no? Greater than or equals to 1. Right? Arithmetic multiplicity should be greater than or equals to 1. That means at least once it will be repeated. No, if I am saying that lambda equals to 4 is one of the eigenvalue, that means it is coming once. If 4, 4 is the eigenvalue, that means it is coming twice. If 4, 4 is the eigenvalue, then that means it is coming thrice. So it has to be greater than or equals to 1, no? If it is coming once, then at least once it is coming, no? So arithmetic multiplicity would be at least 1, and it will be surely greater than or equals to geometric multiplicity as well, right? Total number of independent eigenvectors, what that would be? That would be the summation of geometric multiplicity of each eigenvalue. What does that mean? Let's just say that means simply we are having eigenvalues lambda 1, okay, lambda 2 and lambda 3. So what I will find out? I will find out the geometric multiplicity of A minus lambda 1 I, okay. Then I will find out the geometric multiplicity of A minus lambda 2 I, and then I will find out the geometric multiplicity of A minus lambda 3I. So let's just say here I go to geometric multiplicity 1, 1, 1. So here one independent eigenvector I am having, here also one independent eigenvector I am having, here also one independent eigenvector I am having. So total 3 independent eigenvectors I will have. So simply I am adding up the geometric multiplicity of each eigenvalue. Geometric multiplicity of each eigenvalue. Okay, and all of them will be eigenvector corresponding to distinct eigenvalues are always linearly independent. All of them will be linearly independent. And maximum how many independent eigenvectors I can have? maximum I can have n independent eigenvectors. Why is that so? Because with respect to lambda 1, let's just say lambda 1 is repeated twice, so maximum I can get 2 independent eigenvectors. Here 1 independent eigenvectors and here 1 independent eigenvectors. So total I can have 4 independent eigenvectors. That means basically if there is a matrix of order n cross n, then you can get maximum n different eigenvalues. And let's just say if all are different, then maximum n different eigenvectors. Say yes or no? It is pretty obvious and very easy to understand. Maximum n different eigenvalues I can get and maximum n different eigenvectors I can get. Understandable? Let's solve this question. So this is a new concept now, okay? It is a new concept. New concept we are learning. So previously we have studied 10 properties and we have proved all the 10 properties intuitively as well with respect to the example as well. So everything is crystal clear. So this 2 hour of discussion is giving us all the knowledge or maximum knowledge about the eigenvalues and eigenvectors. Understandable? Let's see this question. A is an invertible matrix and suppose lambda is an eigenvalue of A with the corresponding eigenvector x. Then you need to determine the eigenvalues of the following matrices in terms of lambda. And also you need to tell the eigenvectors as well. What they are saying is that what is given? Given is Ax equals to lambda x. This is given. Okay. Now what you are supposed to find out? Find out the eigenvalue and eigenvector of new matrix which is B, A square. Okay. So basically they are saying that By would be equals to some lambda y. Here if I am calling this as lambda, so let's call it some alpha. So By should be equals to alpha y. So what will be the value of alpha in terms of lambda and what will be the value of y in terms of x? This is what you are supposed to find out. Okay. So what I will do, I need to make A square, no? I need to make A square. So what I will do, here multiply with A. Multiply pre-multiplication by A on both of the side. Pre-multiplication by A on both of the side. So A multiply with A, multiply with x, x multiply with A, multiply with x, right? Now A into A will become A square into x. Now why I have taken lambda outside? Basically someone would say that lambda into x you need to multiply pre-multiplication, no? But lambda is a constant value, so that can be taken outside. Now what is Ax? I know that sir Ax is nothing but lambda x only. Ax is nothing but lambda x, so this is lambda. Ax is nothing but lambda x, so again lambda x. So what this will become? Lambda square x. So what you can see here is that a square x, a square multiply with x is coming out to be lambda square multiply with x. This is what you are getting. A square multiply with x you are getting equals to lambda square multiply with x. What does that mean? There was a matrix B, you multiply that matrix B with some vector x, you got the vector x again with some constant value. So this is the eigenvalue. And this is the eigenvector. Say yes or no? So what you can conclude? If A was having the eigenvalue of lambda and eigenvector of x, A was having the eigenvalue of lambda and eigenvector of x, then A square will have the eigenvalue of lambda square and eigenvector of x only. Do you understand this point or not? And this can be generalized for any n belongs to integer. Any n belongs to integer. Why it can be generalized? So let's check that out. For a to the power 3. For a to the power 3, what will be the scenario? So what is given? Given is Ax equals to lambda x. What I need to make? I need to make a to the power 3. So what I will do? I will multiply with a square here. What I will do? I will multiply with a square here. So what I will get? This will become a to the power 3x. Let's check about this. So this is a square. So a square could be written as a into ax, right? A square can be written as a into x. A into x. So what will be this ax? Ax will be nothing but lambda x only. Now lambda is constant, so that can be taken outside. So lambda square ax. Now again ax could be written as lambda x only. This is already lambda square, ax could be written as lambda x only. So again lambda could be taken outside, so this will become lambda cube x. So a cube x, ax given as lambda x, so a cube x. I hope you understand. Multiply with a square on both of the side, pre-multiplication, a square, a square. What is the meaning of a square? A multiply with a. A multiply with a could be written as lambda x, lambda is taken outside, lambda square ax, ax is written as lambda x, so lambda taken outside, lambda cube x. So a cube x is given as lambda cube x. What does that mean? This was some matrix B or this was some matrix C, multiply with some matrix X, what you got? You got some constant value X. So what is this? This is the eigenvalue. And what is this? This is the eigenvalue. And what is this? This is known as eigenvector. Okay. So what you have understood, that if there is matrix A which is having eigenvalue of lambda and eigenvector of x, then A square will have an eigenvalue of lambda and eigenvalue of lambda square and eigenvector of x. So similarly, A to the power n will have an eigenvalue of lambda to the power n and eigenvector of x only. Eigenvector will not change, but eigenvalue will keep on changing just by the square. A is lambda, a square, lambda square, a to the power n, lambda to the power n. If someone asks you for a to the power minus 1, then a to the power a is having an eigenvector of eigenvalue of lambda and eigenvector of x. Then a to the power minus 1 will have a eigenvalue of lambda to the power minus 1 and eigenvector of x only. What is lambda to the power minus 1? Lambda to the power minus 1 could be written as 1 by lambda. So if I am saying that matrix A is having eigenvalues of 2, 2, 3, so what will be the eigenvalues of A inverse? You will say, sir, 1 by 2, 1 by 2 and 1 by 3. Just the inverse of it. There you go. Understandable? Okay, we can prove it as well. Let's prove it. Let's prove this one. Let's prove it. So what I will do, I will add up a page. Do we have the page? This page we will need to take. So what is given? Ax equals to lambda x is given. Ax equals to lambda x is given, right? I need to make something about A inverse. So what I do, on both of the side I multiply with A inverse. Pre-multiplication of A inverse. Pre-multiplication of A inverse. Now what this will become? A inverse into A will be I. So this will become x lambda into A inverse x. Let's take this lambda here. So what I will be getting? So from this equation what I will be getting is A inverse x I am keeping as it is. A inverse x. This A inverse x I am keeping as it is. Lambda goes downward. So what this will become? 1 by lambda into x. So what you can sense here, there was a matrix A inverse. I multiplied some vector x. I got vector x in return. Multiply with some constant value which is 1 by lambda. What does that mean? If A was having a lambda and x, then A inverse is having 1 by lambda and x. Okay. So this goes on for A inverse as well. What about adjoint A? What about adjoint A? So before adjoint A, let's understand another thing, that again what is given? Given is that Ax is having an eigenvalue of lambda and eigenvector of x. A is having an eigenvalue of lambda and eigenvector of x. Now I need to comment about Ka. Okay, I need to comment about Ka, where K is a scalar. Where K is a scalar or constant value. K is a scalar or constant value. Understandable? So Ax equals to lambda x is given. What I do? K is a scalar, no? So I can multiply with K. K into lambda into x. Directly you can see that you are having a matrix K, which was multiplied with the vector x. What you got? You got vector x in return. What you got? You got vector x in return and then K into lambda only. You are having a matrix K multiplied with vector x, you got vector x in return, which is being multiplied with the factor of K into lambda. What does that mean? If A was having a eigenvalue of lambda and eigenvector of x, then Ka will have eigenvalue of K lambda and eigenvector of x only. There you go. So A is having an eigenvalue of lambda, then K will have an value of k lambda and eigenvector of x. Understandable? So this also we have proved. What about a plus I? What about a plus I? So next again what is given? Ax equals to cx is given. What I need to comment on? A plus some constant value ci. This is what they are asking, no? A plus ci, yes. So I need to comment on a plus ci. This is my target. Understandable? Right? So what do I do? Yes. So what do I do is that on both of the side, I am adding cx. On both of the side, what I am doing? I am adding cx, not cx. I am adding a plus ci is the matrix I need to make. Ax equals to lambda x is given. No, what I am doing? Ax equals to lambda x is given, right? Ax equals to lambda x because lambda is the eigenvalue and x is the eigenvector. Now I need to comment on a plus ci, right? This is what I need to comment on, where c is the scalar. Where c is the scalar. Understandable? So what I am doing? I am adding cx on both of the side. If I add cx on both of the side, what I am getting? Here I can take x as a common. X as common. So will I write down a plus c? No. A is a matrix and c is a constant value. So what I will write down? A plus ci, right? And here what I am doing? Here I am taking x as common. So what I will write down here? Here I will write down lambda plus c only. Why is that so? Why I am writing down lambda plus c? Because sir, why you are writing down lambda plus c, sir? Because lambda is also a scalar value and c is also a scalar value. Lambda is a scalar value only, no? Lambda equals to 2, lambda equals to 3 and c is also a scalar value. So what you can understand? There was a matrix a plus ci. There was a matrix a plus ci which was multiplied with vector x. In return you got vector x only. That was multiplied with vector x. In return you got vector x only, but that was multiplied with the constant value of lambda plus c. So what you understood here, if a is having a eigenvalue lambda with eigenvector x, then a plus ci will have a eigenvalue of lambda plus c and eigenvector is not changing, which is x only. Is that understandable to you? So this point also we have proven. So all of these things we have seen. Let's talk about adjoint A. What is adjoint A? Do you remember this thing? A into adjoint A is nothing but this. So adjoint A would be nothing but. So it is nothing but determinant of A inverse. If A inverse is having an eigenvalue of 1 by lambda and eigenvector of x. Why it will have eigenvalue of 1 by lambda and eigenvector of x? That you already know, because if A is having eigenvalue of lambda and eigenvector of x, then A inverse will have eigenvalue of 1 by lambda and eigenvector of x only. Then if I multiply this A inverse with the constant value, I multiply this A inverse with a constant value. What is the constant value? Determinant of A. Determinant of A will be a constant value, no? 2, 3, minus 1, whatever it is. It will be a constant value. Then what will happen to the eigenvector? Have we seen it? K. If A was the eigenvalue, if A was having eigenvalue of lambda, then K was having eigenvalue of K into lambda. So if A inverse is having an eigenvalue of 1 by lambda, then determinant of A multiplied with A inverse will have an eigenvalue of this and eigenvectors remains the same. So here what you can understand, if I write down the results of everyone, what will be the scenario? Eigenvalue will be lambda square, eigenvector will be x. What will be the scenario here? Eigenvalue will be lambda to the power n, eigenvector will be x. What will be the scenario here? Eigenvalue will be lambda to the power minus 1 and eigenvector would be x. What will be the scenario here? Eigenvalue is coming out to be determinant of A divided by lambda. Do you need to mug it up? Absolutely not. Determinant of A divided by or multiply with lambda inverse. Multiply with lambda inverse and eigenvector of x only. And what will be the scenario here? Eigenvalue is coming out to be k multiply with eigenvalue of lambda and eigenvector of x. And here it is coming out to be eigenvalue of A was lambda plus eigenvalue of ci was c only, and this is the scenario. Is it tough to remember? Absolutely not. Absolutely not. It is not tough to remember at all. Is that clear to you? Okay. So let's solve this question. From this property only we are solving this question. That matrix B is given as 3a square plus 12a minus 4i, you need to find out the determinant of B. A is a 3 cross 3 matrix, then what will be the order of B? A square means it will be a 3 cross 3 matrix. This will also be a 3 cross 3 matrix, and I is also a 3 cross 3 matrix, right? So determinant of order of B will be 3 cross 3. That means it will have 3 eigenvalues, lambda 1, lambda 2 and lambda 3. It will have 3 eigenvalues. Understandable? And what will be the determinant of B? That will be simply the multiplication of these eigenvalues. So what I am supposed to find out? I am supposed to find out the eigenvalues of B. A is having an eigenvalue of lambda with eigenvector x. A square will have an eigenvalue of lambda square. A is already given. And what will be the eigenvalue of I? Identity matrix have eigenvalue unity. What is identity matrix? This is identity matrix. So all the eigenvalues of identity matrix will be 1 only. Okay. And let's not talk about the eigenvector. They are in the addition. So forget about all those things. So basically, what is your matrix B is given? B is given as 3a square plus 12a minus 4i. So eigenvalue of B will be equals to thrice of eigenvalue of A square plus twice of eigenvalue of A minus 4. What is the eigenvalue of I? That is 1 only. That's it. Eigenvalue of B will be thrice of lambda A square plus 12 times of lambda A minus 4 into 1. Eigenvalue of I is 1 only. Is that clear to you? This is the thing that we did here, no? This was A square. A square will have lambda square. A inverse will have lambda to the power minus 1. A plus Ci will have lambda plus C. So similar thing we are doing here. A square is having eigenvalue of lambda A square. 12a will have the eigenvalue of 12a minus 4i. And whatever the operation is there in between, plus operation is there, so plus operation I have put. Here there is minus operation, so minus operation I have put. Understandable? Very straightforward thing. So if lambda A equals to, what all are the eigenvalues? Lambda A equals to 2. So if lambda A equals to 2, then what will be lambda B? So this will be 2 into 2, 4, 12 plus 24 minus 4. What answer we are getting? 32. And if lambda A equals to 3, if lambda equals to 3, so what will be the lambda B? 3 into 3, 9, 27 plus 36 minus 4. So 32 plus 27, that will be 59. So what all eigenvalues you are having? For matrix B, what all eigenvalues you will have? What all eigenvalues you will have? You will have 32 as eigenvalue and 59 as an eigenvalue. Is that correct? No. If it is repeated twice, then 32 is also repeated twice. So 32 multiply with 32 multiply with 9 multiply with 59. So these are the eigenvalues. So what will be the determinant of B? You can do the multiplication on your own. 32 multiply with 32 multiply with 59. So what answer you are getting? 6416. This is the answer you will get. 6416. Okay, you can do the multiplication. This is the answer you will be getting. Let's check back the calculation. 2, 4, 12, 24. 4 into 12, 24 plus 12, 36, 36 minus 4, 32. And here 3 if I put 9, 27, 36, 27 plus 36 minus 4, 32, 3, 2, 5, 2, 7, 59. Yes, so do the multiplication, you will get the determinant of B. Very simple thing, no? Very straightforward. There is nothing in this question that you don't know. If I know the eigenvalues of A, then I know the eigenvalues of B as well. That will be simply 3 lambda square plus 2 lambda minus 4. So what, keep on putting up the value of lambda. Understandable? And whatever the eigenvector you are having with respect to lambda, let's just say with respect to lambda 2, lambda equals to 2, we are having eigenvector V1. And here we are having eigenvector V2. So what will be the eigenvector of B? Eigenvector of B will also be V1 and V2 only. So this you will get with respect to eigenvalue 32. And this you will get with respect to eigenvalue 59. So in matrix B, with respect to eigenvalue 59, you are having eigenvector V2, which is same as matrix A is having a eigenvalue 3, and with respect to eigenvalue 3, you are having eigenvector V2. So eigenvectors are not changing. Eigenvector remains the same. Eigenvalues are simply becoming square, and here simply the value and minus 4. Eigenvector are not changing. For a to the power n, these are the cases of a to the power n or ka. A multiplied with some constant value. Have I talked about A transpose here? Have I talked about A transpose? No, I did not talk about A transpose. Can anyone comment on the eigenvalue of A transpose? If A is having a eigenvalue of lambda, what will be the eigenvalue of A transpose? That will also be lambda only, no? 2, 3, 4, 5. You, for finding out the eigenvalue, what you will do? Multiply minus lambda and then you calculate the determinant. If I take the transpose of this, so what? If I take the transpose, what will happen? Same determinant I will get, no? What is the determinant of A? That is equal to the determinant of A transpose. Say yes or no? Right? So, eigenvalue of A is lambda, then eigenvalue of A transpose will also be lambda. But what about the eigenvector? What about the eigenvector? This may change. This may change. Eigenvector may change. Okay? So, we will see this point. We will see this point, don't worry. But for with respect to eigenvalue, you can understand on your own. A is having an eigenvalue of lambda. So A transpose will also have the eigenvalue of lambda only. There is no point in thinking too much, right? A is having eigenvalue of lambda, then A transpose, if you are simply taking the transpose, it will not change the determinant. Determinant will be same. Characteristic equation will also be same. Roots of characteristic equation will also be same. That means eigenvalue will be same, but eigenvector may change. Eigenvector may change. Why is that so? Because Ax equals to lambda x will be there, no? Now if I take transpose on both of the side, if I need to make transpose, then I will have to take transpose here. I will have to take transpose. So if I am taking transpose on both of the side, what I will get? X transpose into A transpose, lambda as it is, multiply with X transpose. So A transpose multiply with some X transpose is giving you X transpose multiply with the lambda. Is that statement correct? No. That statement is wrong. Why it is wrong? Because A transpose should have been multiplied with some constant matrix X here, but X transpose is coming beforehand. Are you able to understand what I am saying? Say yes or no? A transpose, X transpose is coming here. It should have come here. If it was coming later on, then I could have said that A transpose is being multiplied with some matrix which is X transpose and some constant value X transpose I am getting. What does that mean? This is my eigenvector, this is my eigenvector and this is my eigenvalue. But it is wrong. X transpose is coming beforehand. So you cannot comment on the eigenvector of A transpose. Are you able to understand this point? Basically, conclusion is here only. I will not teach it later on. The only conclusion is that if A is having a eigenvalue of lambda and eigenvector of x, then A transpose will have an eigenvalue of lambda only, but eigenvector of y, which we cannot comment. There is no relation between y and x. Is that understandable to you or not? A is having an eigenvalue of lambda and eigenvector of x, then A transpose will have an eigenvalue of lambda only. Why eigenvalue lambda? That is pretty understandable to you. If you take the transpose, determinant will not change, characteristic equation will not change, the same value of lambda you will be getting, but eigenvector you cannot comment. So only for A transpose you need to remember, but for all of them eigenvector will be same. It is a very, very important point. People focus on eigenvalues as only, but if I need to frame a good question in the examination, I will frame it on eigenvectors. I will ask them what will be the eigenvector corresponding to that particular value. Let us say A is having a eigenvalue of 2 and 3 and they are saying that with respect to 2 you are having eigenvector v1 and here you are having eigenvector v2. So now A square will be having a eigenvalue of 4 and 9. So what will be the eigenvector corresponding to eigenvalue 9? So answer would be sir v2 only, and here it will be v1. So eigenvector will not change. Okay, corresponding eigenvectors will not change, but eigenvalues will be changing, and how they will be changing, that also we know. So this question we have seen, right? Now we need to study about Cayley-Hamilton theorem. Okay, Cayley-Hamilton theorem. This theorem we will study, but before that, let's see some basic prerequisites, very basic prerequisites that you already know about the quadratic equation. Here I will be talking about the roots, addition of roots, multiplication of roots. Here also I will talk about the roots, addition of roots and multiplication of roots. And similarly, we will write down the characteristic equation for 2 cross 2 matrix by our conventional method. After that, I will tell you a short trick, and then we will study about Cayley-Hamilton theorem. Understandable? So till this point, on top level, we have seen these 10 properties. First, we saw these 10 properties, and this also you can treat as a separate property only. This is also a separate property, that A is having eigenvalue of lambda, then A square is having eigenvalue of lambda square. A to the power n will have the eigenvalue of lambda to the power n. A inverse will have the eigenvalue of 1 by lambda. Adjoint A will have the eigenvalue of determinant of A divided by lambda. K will have the eigenvalue of K into lambda. A plus Ci will have the eigenvalue of lambda plus C. All the eigenvectors would be same. All these will be same. Understandable? And then we saw this particular question. Now we will talk about basics of quadratic equation after a break. I will take a break and then I will come back and we will talk about the basics of a quadratic equation. I hope you are enjoying the actual depth of eigenvalue and eigenvector. This is the actual depth. Otherwise, I could have taught on the surface level that this is how you find out the eigenvalues, eigenvectors, independent eigenvectors, all those I could have skipped, right? But you are actually understanding the depth of eigenvalue and eigenvector. I hope you understand. Let's study about basic quadratic equation after a break. Yeah, welcome back. So let's study about quadratic equations. Basic quadratic equation we will see, then basic cubic equation also we will see. So this is your quadratic equation. Can I write down this equation in this manner, that I am taking a as common? So if I take a as common, what I will get? X square plus b by a plus c by a equals to 0. Is it a quadratic equation? Yes, sir. You have just taken a as common. A goes to 0. This will become 0 by a. That will be equal to 0 only. So sir, it is a quadratic equation. That means it will have two roots, alpha and beta. So it will have, sir, two roots. What will be the addition of the roots? Sir, addition of the roots is given by simply this value with the negative sign, and multiplication of the roots will be given by simply this value with the positive sign. I hope you know this thing. In basic elementary classes you might have studied this, right? This is not very tough to remember. Similarly, what I can do is that I can write down this equation as x cube plus b by a x square plus c by a x plus d by a equals to 0. Is it a cubic equation? Yes, sir. How many roots it will have? 3 roots it will have, alpha, beta, gamma. Understandable? So what will be the addition of roots? The addition of roots will be this value with the negative sign. And what will be the multiplication of roots? So here the multiplication of roots will be, this is d by a, right? D by a, but with the negative sign. So basically, when you write down the addition of roots, always negative sign will come up. But in case of multiplication of the roots, negative sign would come up if the maximum power is odd. And if the maximum power is even, then here positive sign would come up. Is that clear to you? We will write it down, but as of now, can you try remembering it? That here negative sign, for addition of roots, always negative sign would come up. For multiplication of roots, negative sign would come up if the maximum power is odd. If the maximum power is even, then positive sign would come up. And always make sure that you will make the coefficient of maximum power 1. Then only you will write down the values. Let's just say question is given 4x cube plus 2x square plus 3x plus 1 equals to 0. And you are supposed to find out how many roots it will have, alpha, beta, gamma. So you are supposed to find out the multiplication of roots. What will be the answer? 1? No. The final value I need to check, but divide by 4 you do. Divide by 4 you do. Divide by 4 you do. So answer would be 1 by 4. What is the maximum power here? Odd. So minus sign. So multiplication of the roots will be minus 1 by 4. Is that clear to you? What will be the addition of roots? Alpha plus beta plus gamma. Addition of roots, always this value but with the negative sign. So minus 2 by 4. Is that clear to you? Understandable? So always make sure that first I will make the coefficient 1 here and then I will comment. Sir, what does this represent here? C by A. So C by A represent alpha into beta plus beta into gamma plus gamma into alpha. That will be C by A. Although it is not a matter of concern for you, you don't need to remember it. Only thing you need to remember, addition of roots and multiplication of roots. Let's just say I write down the equation in terms of power n. Okay. So next would be x to the power n minus 1. Next would be x to the power n minus 2. And it will keep on going. And let's just say last constant value is d. That is equal to 0. So this is the equation in power n. So what is the first thing that I will do? I will make this coefficient as 1. So I will have to divide by a. I will have to divide by a. I will have to divide by a. So this divide I have done. What will be the addition? Like how many roots it will have? It will have n root. It will have n roots, right? Alpha 1, alpha 2 and total n roots it will have. So what will be the addition of roots? So alpha 1 plus alpha 2 dot 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 alpha n. Addition of roots will be this value b by a with the negative sign. Always, right? And what will be the multiplication of roots? Sir, multiplication of roots will be this value which is d by a. So multiplication of roots will be, sir, d by a. But it can have minus d by a as well. multiplication of roots will be, sir, last constant value, but it can have the value as minus d by a as well. When it will have minus d by a? If n is odd, and if n is even, then it will be plus d by a. That's it. This is what we have written. So always at least remember for quadratic and cubic. If you remember for quadratic and cubic, you will be able to make for power n as well. Very, very, very important. Okay, always very, very, very important. Only addition and multiplication is important. Why is that so? Because we are going to make a characteristic equation. For the determinant, for the matrix, we will make the characteristic equation. The characteristic equation will be of this form only. So there I will be able to tell that this will be the trace of A, and this will be the determinant of A, right? Isn't it the trace of A? And isn't it the determinant of A? So will you be able to remember whatever the equation is written, write that equation down in the form such that here the maximum power is having coefficient 1. Then just next value, that will represent the trace of A, that will represent the trace. Okay, simply b by a with the negative sign, and the last value will represent the determinant. You just need to check if the power is even or odd. If the power is even, then simply the positive sign, otherwise the negative sign. Understandable? Straightforward? Okay. Can you write down the characteristic equation of this 2 cross 2 matrix? Sir, if I need to write down the characteristic equation, I know that, sir, characteristic equation is given by this thing. So what I will do? Sir, I will 2 minus lambda, 2, 1, 3 minus lambda equals to 0. Can I find out the determinant, sir? Yes, sir. 2 minus lambda multiply with 3 minus lambda minus 2 equals to 0. If I take minus common from here, from both of the end, I am taking minus common. So can I write this down as 2 minus lambda into 2 lambda minus 3 equals to 0? Lambda minus 2, because I have taken negative sign. From lambda minus 3 also I have taken negative sign. So negative sign multiply with negative sign, this will become positive sign, right? So now just simply solve it. So lambda square minus 5 lambda plus 6 minus 2 equals to 0. So lambda square minus 5 lambda plus 4 equals to 0. Okay, lambda square minus 5 lambda plus 4 equals to 0. This is the characteristic equation I am getting. Understandable? Another thing, someone can say that, sir, I know the trace of A. I know that trace of A. I know that trace of A. What will be the trace of A? So trace of A is 5. Sir, I know that, and I am writing this down as trace of A. Sir, I know the determinant of A as well. Determinant of A. Sir, what is the determinant? 6 minus 2, that will be 4. So determinant of A also I know. Sir, I know that if I am writing down the characteristic equation, it will be of the quadratic form. Why it will be of the quadratic form? Because this is the matrix of 2 cross 2. So for 2 cross 2 matrix, you can write down your quadratic equation in this manner. Lambda square minus trace of A multiply with lambda plus determinant of A equals to 0. So lambda square minus trace of A. What is the trace of A? 5 plus determinant of A, that is 4, equals to 0. There you go. So this you need to remember. Okay. So for a 2 cross 2 matrix, quickly how will I write down the characteristic equation? So lambda square minus trace is 5 plus 3 into 2 6 minus 2 4 equals to 0. That's it. You will not do all this process. Understandable? All good? And can you let me know what is this 5 is representing? I told you lambda 1 plus lambda 2. If this equation is having 2 roots, which are lambda 1 and lambda 2. So addition of roots will be given by this value multiply with a negative sign. So minus 5 multiply with another negative sign, it will become plus 5. And lambda 1 into lambda 2, what will be? That will be the last value. Now you need to check the power. Power is even, that's why positive sign would come up. So lambda 1 plus lambda 2, addition of lambda 1 and lambda 2. That means these are the eigenvalues, no? Addition of eigenvalues is represented by the trace only. So is it the trace? Yes, sir. And multiplication of the eigenvalues is represented by the determinant. So is it the determinant? Yes, sir. This is also the determinant. There you. Trace is also there. Determinant is also there. So is there any issue? Absolutely not. Say yes or no. Right? So shortcut you have understood. Lambda square minus trace of A into lambda plus determinant of A. So can you write down? Now we will study about the Cayley-Hamilton theorem. We will study about it, but let's just write down the characteristic equation of this matrix A. Can you write down the characteristic equation? Yes, sir. Characteristic equation will be lambda square minus trace of A, 3 plus 2, 5, plus determinant of A, 4 equals to 0. Okay, this was the same matrix. Yeah. So can you write down the equation? Yes. Now what Cayley-Hamilton theorem will say, that every square matrix satisfy its own characteristic equation. What does that mean? This is the characteristic equation is there, no? In place of lambda, simply put a square minus, in place of lambda simply put a plus 4. This is a matrix, this is a matrix, so in the addition matrix should be there, no? So 4 alone, 4 is a scalar value, that cannot come, so 4i equals to 0. So this will, that is equals to 0 matrix. Basically lambda was a value, lambda square was a scalar value, lambda was a scalar value. In place of lambda I am putting matrix A. This is your matrix A. What I am putting matrix A. So basically you take the matrix A and do its square. What is the meaning of A square? A square simply means matrix A multiply with matrix A. Then minus 5 multiply with matrix A plus 4, and here I will write down matrix I. Matrix I. That will be equals to 0 matrix. Okay. So you try doing it on your own and you will get to know that yes, this equation will be satisfied. What you do is that you find out A square. What will be A square? So 2, 2, 1, 3 multiply with 2, 2, 1, 3. So what answer you will be getting? 2, 2, 4, 6. In that manner you can do the calculation. You will get value of A square. Then you find out 5a. Then you subtract from here and then you add 4i from there. Okay. So you will get to know that it is coming out to be 0, 0, 0. So this is what it will say, that whatever the characteristic equation, if you are having the characteristic equation, then you can simply write down this particular thing plus 4i, that will be equals to 0. Understandable? Okay. How it can be useful? Can you let me know the value of a cube here? What I need to find out? I need to find out the value of a cube. Value of a cube. So what I am doing, let's just say this is equation 1. On both of the side I am multiplying with a. Pre-multiplication I am doing. Pre-multiplication of a I am doing. So this will become a square. Sorry, a cube. This will become a square. This will be 4 into a into I. That will be 4a. And a into 0 will be 0 only. Is that clear to you? Pre-multiplication of a I have done. In this equation, pre-multiplication of a. Pre-multiplication of a I have done. Understandable? So this is my a cube. What is the value of a square? From here, what is the value of a square? A square is nothing but 5a minus 4i. So a square is nothing but 5a minus 4i plus 4a equals to 0. So a cube minus 25a plus 20i plus 4a equals to 0. So what is the value of a cube you are getting? A cube you are getting is 21a minus 20i. Is that clear to you? This is the value of a cube you are getting. And this is the value of a square you are getting. A square was 5a minus 4i. What is a cube? Multiply with a cube here. 5a square 4a. 5a square will be 5a minus 4i plus 4a. So 25a plus 20i plus 4a. So this will become minus 21a plus 20i. So 21a. So this is the equation that you are getting. Can you find out value of a to the power 4? A to the power 4. So pre-multiplication of a on both of the sides. What I am doing here, this is 20i. So again what I am doing is that I am doing the pre-multiplication of a on both of the sides. So what it will become? It will become 21a square minus 20i. Right? 21a square minus 20i into a. So this will become minus 21a square into a. Now what is the value of a square? So value of a square is 5a minus 4i. 5a minus 4i minus 20a. So if you solve it, what you are getting? Whatever that I am getting, that is not my matter of concern. I want to just prove something here. This will be 84 minus 20a. Okay. So this is coming out to be your a to the power 4. So from here I can sense that a to the power 4 is coming out to be nothing but 85a minus 84i. This is your a to the power 4. So a to the power 4 is written in this manner. What is that? ai. So we will make a conclusion, but as of now you just need to see the results, that this is how I can write down a to the power 4. This is how I can write down a to the power 2. Understandable? This is how I can write down a to the power 2. A to the power 2, a to the power 3, a to the power 4. Okay, we will make a conclusion. Have some patience. Let's do the same for 3 cross 3 matrix. So for this 3 cross 3 matrix, I got to know that this is my characteristic equation. Sir, how did you find it out? By doing a minus lambda equals to 0. So this characteristic equation I got. So that you can do on your own. So if this is the characteristic equation I am getting, then I know that in place of lambda I can simply replace a. This will also be satisfied. So can you write down the value of a cube here? Yes sir, value of a cube is coming out to be 3a square minus 3a plus 3i. This is the value of a cube you are getting. Can you find out the value of a to the power 4? Yes sir, I can find out the value of a to the power 4. So that would come out to be pre-multiplication of a I am doing. So minus 3a square plus 3a it would be. So 3 into a cube will be 3a square minus 3a plus 3i minus 3a square plus 3a. So 9a square minus 9a plus 3i minus 3a square plus 3a. So 3a square minus this will become 6a square minus 9a plus 3a, what you are getting, minus 6a plus 3i. This is your a to the power 4 you are getting. This is the value of a to the power 4 you are getting. 6a square minus 6a plus 3i. Similarly, what will be the value of a to the power 5? So for a to the power 5 you can multiply again 6a cube 6a square plus 3a. Here what I have done, I have multiplied with a, right? So this will become a to the power 5, this will become 6a cube and so on. So in place of a cube, what you will write down? 3a square minus 3a plus 3i minus 6a square plus 3a. So 18a square minus 18a plus 18i minus 6a square plus 3a. 12a square minus 15a plus 18i. There might be some error in calculation, forget about the calculation and all those things. I want to prove some point here. So here a to the power 3, 3a square something, a to the power 4, 6a square something, a to the power 5, 12a square something. Here a to the power 2 was 5a something, a to the power 3 was 21a something, a to the power 4 was 85a something. What you understood? This was a 2 cross 2 matrix. Any higher power of a I could have written in terms of a and identity matrix. This is a 3 cross 3 matrix. Any higher power of a I could have written in terms of a square, a and I. Are you able to understand this point? For a 2 cross 2 matrix, any higher power of a, okay, where k is greater than or equals to 2. Here I have written a square, no? A square. So that I could have written in terms of c1a plus c2 into I. Any higher power where k is greater than or equals to 3 cross 3 matrix, I could have written in terms of, here it is 3, no? So it will become a to the power 2 plus c2 into a plus c3 into I. This is the, like, everyone would teach this Cayley-Hamilton theorem. This everyone would teach, but I don't know why this topic is not taught. So this is the second statement of Cayley-Hamilton theorem. This is the first statement, that lambda could be replaced with a. But one interesting observation we saw here, that if I am calculating a square or a cube or a to the power 4, one strong thing I am noticing, what I am noticing, that no matter whatever the power is, that could be written in terms of a and I, because it was a 2 cross 2 matrix. So let's just say if this was n, then this was n minus 1. Here the power was n minus 1, right? So similarly, if this is 3 cross 3, so here the power is n minus 1 as well, which is 2. So for n cross n matrix, what I will do? A to the power k, where k is greater than or equals to this value, which is n. So a to the power k would be c1 a to the power, this was n, this was 3, so 3 would come as 2, a to the power n minus 1 plus c2 a to the power n minus 2 and so on till cn I. So in statement someday this particular thing could be written for Cayley-Hamilton theorem. For Cayley-Hamilton theorem, which of the following statements are true? For a 2 cross 2 matrix, a to the power k, for k greater than equals to 2, it could be written as c1a plus c2i. What I have seen is that in a somewhere, like, forget about it, this is the concept, okay, like the misconception is there that this particular statement is written for any kind of matrix. No, this particular statement could be written only for 2 cross 2 matrix only. this could be written only for 3 cross 3 matrix, and this could be written only for n cross n matrix. Are you able to understand this point? Usually what has happened in the gate examination, the question has always come on 2 cross 2 matrix. So people think that this particular statement would work for any n cross n matrix. No. Are you able to understand this point? Here I have got the value of a to the power 3 as 3a square minus 3a plus 3i. That's it. I cannot reduce it more. This is the maximum reduction that I can do. So here a to the power 2 would come. So if I am asking about 5 cross 5, if let's just say there is 5 cross 5 matrix, then any higher power, let's just say a to the power 9 could be written as c1 into this is 5 a to the power 4 plus c2 into a to the power 3. So let's write down this example only. So for 5 cross 5 matrix, for 5 cross 5 matrix, a to the power 99 could be written as c1, this is 5 no, so here one lesser value will come, plus c2 plus c3 plus c4 and plus c5. There you go. This is how we can write down. But saying this particular thing, that is wrong. So you cannot write down a to the power 5 as a to the power 5, sorry, not a to the power 99. Here a to the power 99 cannot be written in terms of c1a plus c2i. This is wrong. Okay, this you cannot write down. So the problem is that in all the time, everywhere, the question has always been asked on 2 cross 2 matrix. So since the question has been asked on 2 cross 2 matrix, so people have made this particular statement for any n cross n matrix. But no, for 3 cross 3, this will be the scenario. For n cross n, this would be the scenario. For 5 cross 5, this will be the scenario. For 2 cross 2, this will be the scenario. Whatever that n value is there, here the power n minus 1 would be there. Okay. So always remember this particular thing. So in Cayley-Hamilton theorem, if you just able to write down the characteristic equation, then your job is done. If I am able to write down the characteristic equation, then this is how I can satisfy the condition. And after that, I go to know one more thing, which is this particular slide. That a to the power k could be written as c1a plus c2i in terms of 2 cross 2. In case of 3 cross 3, it could be written as c1a square plus c2a plus c3i. In case of 5 cross 5, it could be written as c1a to the power 4 plus c2a cube plus c3a plus c2a cube plus c3a square plus c4a plus c5 into I, and so on. Understandable? Let's solve gate question only. This is not a gate question, this is a question that is framed by me, and then we will solve a gate question. So here a very rough answer you will get. You need to represent a to the power 10 in terms of a and I. Okay, so I would go to know that it is a 2 cross 2 matrix. That means any higher power of a could be written as c1a plus c2i. Now I know one thing. What do I know? That here a I can replace with lambda. Basically, if I know this equation, can I write down the characteristic equation? Yes sir, a I can replace with lambda. What will be the eigenvalue of a to the power 10? That will be lambda to the power 10. C1 into lambda. Basically, wherever you see a, there you can replace lambda. A to the power 10, lambda to the power 10. A, lambda. C1, C2 into what is the eigenvalue of 1? That is 1 only. Sorry, what is the eigenvalue of a identity matrix? That is 1 only. So I can write down the equation that lambda to the power 10 is nothing but C1 lambda to the power C1 lambda to the power 1 plus C2. This is something that I can write down. Is that clear to you? Say yes or no. Now what all are the eigenvalues of this particular matrix? Eigenvalues. Can you find out the eigenvalues? Yes sir, we can find out the eigenvalues. So lambda square, what is the trace? 5 lambda, what is the determinant? 4. If we solve, what we will get? 4 and 1. Right? 4, 16, 20, 1, 1. Yes. So lambda value you will get 1 and 4. So these are the eigenvalues. Now if I put 1 here, 1 would be equals to 1 plus C2, right? And if I put 4 here, so 4 to the power 10 would be equals to 4C1 plus C2. Why I did so? I did so to find out the value of C1 and C2, because I need 2 equations. There are 2 variables, C1 and C2 are the variables. I need 2 equations. I got to know that my eigenvalues are coming 1 and 4. That means they will satisfy this equation, because this is the characteristic equation. So they will satisfy here. So I put 1 here, 1, then I put 1 here, 1 equals to C1 plus C2, then here 4 to the power 10, C1 plus C2. If I subtract both of the equations, what I will get? 3C1 would be equals to 4 to the power 10 minus 1. So value of C1 is coming out to be 4 to the power 10 minus 1 divided by 3. right? And what is the value of C2 you are getting? C2 is 1 minus C1. 1 minus C1. So 1 minus 4 to the power 10 minus 1 divided by 3, right? So 3 minus 4 to the power 10 plus 1 divided by 3. So what is the value of C2 you will get? C1 plus C2 is 1, 1 minus C1, value of C1 I have put 4 to the power 10 minus 1 divided by 3. So 3 I have taken here. So 3 goes here, 3, and then when I open that bracket, so it will become 4 to the power 10 minus 1. So what is the value we are getting? 4 minus 4 to the power 10 divided by 3. So this is the value of C2 we are getting. So C1, C2 we have got. Now using this equation, using this particular equation, I can write down the value. So a to the power 10 would be given as, what is the value of C1? That is 4 to the power 10 4 to the power 10 minus 1 divided by 3 multiply with a plus C2 is, I can take 4 common from here, no? So it will become 4 into 1 minus 4 to the power 9 divided by 3, right? I have taken 4 common. So this will become 1 minus 4 to the power 9 divided by 3 multiply with I. So this is the value of a to the power 10 I can write down. This is the answer. So this could be mentioned in one of the options that a to the power 10 could be expressed as this expression. So will you find out a to the power 10? No. What you will do, you will follow this particular procedure. That's why 2 cross 2, any higher power could be written in this format, and then I can get the answer. Let's solve a gate QIQ. This is a gate question only. If you are able to solve it, then job done. First one is MSQ. Next one is also MSQ or whatever you want to treat. Okay, every question is MSQ. Every question is MSQ. Multiple answer could also be possible. Single answer could also be possible. So can you write down the characteristic equation? Yes, sir. What will be the characteristic equation? Lambda square minus trace of a. What is the trace? Minus 3. So minus minus will become plus. Plus, what is the determinant? Determinant will be 2 equals to 0. Did you understand this point? Lambda square plus 3 lambda plus 2. Did you understand this? Absolutely, sir. Lambda square minus trace. Trace is minus 3. So lambda square plus 3 lambda plus, what is the determinant? Determinant is 2. Minus 3 into 0, 0. Minus 2. So determinant is 2. Right? So from here what I can get? A square plus 3a plus 2i. In place of lambda I can put a. In place of lambda I can put a. So a square plus 3a plus 2i. Now what I can sense? This I could be written as, say yes or no. Right? I am just doing the factorization. Nothing else. So a I can take common. So what I will get? A plus 2i. And here I can take common. So what I will get? A plus 2i. I hope you understand what I am doing. X square plus 3x plus 2. What you will get? Just solve from here. If you just solve from here, can you write down lambda plus 1 into lambda plus 2 equals to 0? Say yes or no. Right? So similar thing I have done here. So from here what I will get? A plus 2i is coming common. So a plus I multiply with a plus 2i is coming out to be 0. So if you write down this equation, lambda plus 1 into lambda plus 2 equals to 0. So in place of lambda you can put a. In place of 1 you can put I. In place of lambda you can put a. In place of 2 you can put 2i equals to 0. The same answer you are getting. Right? So either you do by this method, which feels tougher for you. So what you do is that, do the factorization, write down in this manner lambda plus 1 into lambda plus 2, then replace lambda with a. So what option is matching? This option is matching. A plus I into a plus 2i. But other option may also match. What option may also match? A square plus 3a plus 2i equals to 0 is given. We need to find out the value of, now a square plus 2a plus 2i, will that be equals to 0? No. This option is gone. What is a to the power a? E to the power a. What is e to the power a? Sir, e to the power a is nothing but, this we have already understood in basics, right? So what is the expansion of e to the power x? 1 plus x square by 2. So I plus a square by 2 factorial plus a cube by 3 factorial and so on. Like there is no meaning of this. How it would be equals to 0? No meaning of this. This particular thing is equals to 0, right? So here nothing we can include. So this option is also gone. Let's find out, here we need to find out the value of a inverse. So can I find out the value of a inverse? What I need to do? Multiply a inverse on both of the side. Pre-multiplication I am doing. So this is a inverse I am multiplying. Then a square is nothing but a into a plus 3 a inverse into a plus 2 a inverse into I equals to 0. So a inverse into a will become I into a will become a. plus A inverse into A will become 3i plus A inverse into I will become 2A inverse equals to 0. So A plus 3i plus 2A inverse. A plus 3i plus 2A inverse equals to 0. Or in the examination, they could have simply asked what is the value of A inverse. So that you will say, sir, it is nothing but A plus 3i divided by 2 and with the negative sign. This will be the value of A inverse. Right? You can find out A inverse from here. A inverse goes here. So negative sign would come up. A plus 3i divided by 2. So A and C are correct. And how would you write down A to the power 9? It is a 2 cross 2 matrix. So what you will do? Sir, A to the power 9 could be written as C1a plus C2i. From here what I can sense? Lambda to the power 9 could be written as C1 lambda plus C2. What is the value of lambda? Minus 1 and minus 2. So minus 1 to the power 9. C1 minus 1 plus C2. C1 minus 1 is equals to minus C1 plus C2. Right? This is the first equation we are getting. And then what is the value of lambda? Lambda is minus 2 as well. So if you put minus 2 here in this equation, if I am putting minus 2, so minus 2 to the power 9 equals to C1 into minus 2 plus C2. It is completely mathematics now. There is no concept. The simply mathematics, you need to find out the value of C1, C2. So 2 to the power 9 is 512 minus sign minus 2 C1 plus C2. Right? If I subtract the equation 2 from 1, 1 minus 2 if I do, so what I will get? 511 and this will become C1. So C1 value is coming out to be 511. Okay, and minus 1 minus 511 plus C2. That means C2 value will come out to be 510. So C1 is 511, C2 value is 510. So A to the power 9 is coming out to be C1 is 511A plus C2 is 510I. 510I. This is the value of A to the power 9 you are getting. 511 into A, 510 into I. Where is the question? This is the answer. Understandable? Well and good. Very straightforward. There was another way as well. Like if eigenvalues of A are minus 1 and minus 2. So what will be the eigenvalues of A to the power 9? They will be minus 1 to the power 9 and minus 2 to the power 9. So eigenvalues will be minus 1 to the power 9 will be minus 2 and here this will become minus 512. So A to the power 9 will have eigenvalues of minus 1 and minus 512. Right? These will be the eigenvalues. These will be the eigenvalues. Now you could have checked the option. That which option is having minus 1 and minus 512 as the eigenvalue. First option. What is the first option? First option is saying 511A plus 510I. 510I. So what will be its eigenvalues? Its eigenvalues will be nothing but 511 lambda plus 510. This will be their eigenvalues. Right? This will be their eigenvalues. So here I need to put two values. I need to put lambda equals to minus 1 and lambda equals to minus 2. Right? Lambda equals to minus 1 and lambda equals to minus 2 I need to put. So if I put lambda equals to minus 1, what is the eigenvalue I am getting? Lambda equals to minus 1 if I am putting. So eigenvalue I am getting is minus 1. And if I put lambda equals to minus 2, what eigenvalue I am getting? That I am getting is minus 512. Because 501 into 2, that is 2 to 10. Subtracted from 510, you will be getting 512 only, but with the negative sign. That means the first option is getting these eigenvalues, minus 1 and minus 512. And we are supposed to get these eigenvalues only, minus 1 and minus 512. That means option A would be correct. Understandable? Here if you put, you will not get the answer. Here also you will not get the answer. Here also you will not get the answer. Understandable? Did you understand this question or not? Right? A to the power n you need to find out. So it's simple. By this particular method also you could have find out C1a into C2i. In that manner you can find out. Or if you just want to see by the options. So in the options what you can see directly, you can sense that, sir, if I put up the eigenvalues, this is the first option. What will be the eigenvalues of matrix B, which is equals to 511A plus 510I. So what will be the eigenvalue? So eigenvalue will be 511 into eigenvalue of A plus 510 into eigenvalue of I. Eigenvalue of I is nothing but 1. So 511 lambda plus 510. So put the value of lambda which is -1 and -2 and get the eigenvalues which are same as the eigenvalue of a to the power 9. That means a to the power 9 and this will be equivalent. That's it. Okay, and check rest of the options. If all three you are able to cut, that means A will be the answer. Understandable? Well and good. Let's proceed in the next question. So what this question is saying? Consider a non-singular 2 cross 2 matrix. Now there is question and question only. Okay, for very long time we are going to solve problems only now. Only it's all about questions. Okay, so consider a non-singular 2 cross 2 matrix. Trace of A is given as 4. Trace of A square is given as 5. Determinant of a matrix A you need to find out. Let's just say matrix A is there. It will have two eigenvalues lambda 1 and lambda 2. So what will be the eigenvalues of A square? So that will be lambda 1 square and lambda 2 square. What is given? Trace of A is given. What does that mean? So lambda 1 plus lambda 2 equals to 4 is given. Trace of A square is given. So what is the eigenvalues? Lambda 1 square and lambda 2 square. What does that mean? Lambda 1 square plus lambda 2 square equals to 5 is given. If I do the square on both of the side, what I will get? A square plus B square plus 2AB, that will be equals to 16. What I have done? I have done the square on both of the side. So lambda 1 plus lambda 2 whole square, that will be lambda 1 square plus lambda 2 square plus 2 lambda 1 into lambda 2, that would be equals to 16. Now lambda 1 square plus lambda 2 square is given as 5. So 2 lambda 1 into lambda 2, here it is 5, right? That is equals to 16. If you solve from here, then lambda 1 into lambda 2 is coming out to be 11 by 2, which is 5.5. 5.5, and what is this 5.5? 5.5 is nothing but the determinant of A. Say yes or no. So determinant of A is nothing but 5.5. That is the answer. Very simple question. You just need to find out the value of lambda 1 into lambda 2. What is the determinant of A? So in my mind it will click that, sir, I need the value of lambda 1 in lambda 2. If these two equations are given, I will think, yes, I can find out the value of lambda 1 and lambda 2. How will I do it? I will just simply do the square. Lambda 1 square plus lambda 2 square plus 2 lambda 1 lambda 2. So this will be 5 here. 11 divided by 2, 5.5 will be the answer. There you go. Understandable? Now matrix A is given, matrix B is also given. I is the identity matrix. You need to find out the determinant of B. What is matrix B is given? Matrix B is given as A cube minus A square minus 4A plus 5. This is your matrix B. Okay. And I is the identity matrix. You need to find out the determinant of B. So what I will do? Lambda B is given as lambda A square. What I am saying is that matrix A is having the eigenvalues of lambda A. So, and I am saying that matrix B is having an eigenvalue of lambda B. Understandable? So I am finding the eigenvalues of matrix B. What that would be equivalent to? So that would be equivalent to lambda A cube minus lambda A square minus 4 lambda A plus 5. Say yes or no. Now I need to find out the eigenvalues of matrix A. I need to find out the eigenvalues of matrix A. So how will I find out the eigenvalues of matrix A? Why I need to find out the eigenvalues? Because if I am able to find out the eigenvalue of matrix A, if you know the eigenvalues of matrix A, then you know the eigenvalues of matrix B as well. And if you know the eigenvalues of matrix B, then you know the determinant as well. Because simply if I do the multiplication of all the eigenvalues, then my job would be done. This pi sign means multiplication. So if I do the multiplication of all the eigenvalues of matrix B, then my job would be done. So matrix A is there, find out their eigenvalues. Using those eigenvalues, find out the eigenvalues of matrix B. Whatever the eigenvalues that you are getting, do the multiplication, you will get the determinant of B. Is that understandable to you? Okay, so this is what we need to do. We need to find out the eigenvalue of matrix A. So what those eigenvalues would come out to be? Simply I can sense that eigenvalues will be 1, 2 and minus 2. Eigenvalues of A we need to find out. A we need to find out. So A minus lambda I would be equated to 0. So through the diagonal element I need to subtract lambda. So 1 minus lambda, 2 minus lambda and minus 2 minus lambda. 0 minus 1, 0 minus 1, 0 0. Okay, so what you do the expansion with respect to the last row, right? So with respect to last row, 0 0 will be gone. So here I can see minus 2 minus lambda, 2 minus lambda multiply with 1 minus lambda, right? So values, eigenvalues are coming out to be, eigenvalue of A are coming out to be minus 2, 2 and 1, minus 2, 2 and 1, minus 2, 2 and 1. These are the eigenvalues of A. Now we are supposed to find out the eigenvalues of B. So eigenvalues of B we are finding out. What those eigenvalues will be. So lambda A cube minus lambda A square. So do the cube, then negative sign 4 times, 5 times. So first do the cube, then do the square. First do the cube, then do the square, then minus 4 into minus 2 plus 5. This is the scenario you need to do. Okay, so just take care of the calculation. Here anything that can go wrong is calculation only. So what will be the answer? Minus 8 minus, this will become minus 2 square, that will be 4, right? Plus 8 plus 5, so 1. Yes, other value would be 2 to the power 3 minus 2 to the power 2 minus 4 into 2 plus 5. So 8 minus 4 minus 8 plus 5, again 1. Next would be 1 to the power 3 minus 1 square minus 4 into 1 plus 5. This is 1 minus 1 minus 4 plus 5, again 1. So eigenvalues of lambda B is coming out to be 1 1 1 only. This is the eigenvalues you are getting. These are the eigenvalues you are getting. What does that mean? What will be the determinant? Determinant will be 1 into 1 into 1. Now can anyone tell what will be B? Can anyone tell what will be B? B will be nothing but an identity matrix. Why is that so? Because it is a 3 cross 3 matrix. It is a 3 cross 3 matrix. So B is also a 3 cross 3 matrix, right? B is also a 3 cross 3 matrix, and this is also a 3 cross 3 matrix, and all the eigenvalues are coming out to be 1. So for what kind of matrix we get eigenvalues to be 1? Identity matrix, no? Identity matrix, because identity matrix is a diagonal matrix, and for the diagonal matrix, diagonal elements are the eigenvalues, right? Diagonal elements are the eigenvalues. That's why it would be a identity matrix only. Is it necessary? Is it necessary that B will be identity matrix only? What if B is this matrix? What is B? What if B is this matrix? What all are the eigenvalues here? Is it a lower triangular matrix? It is a lower triangular matrix, right? So what all are the eigenvalues? Sir, it is 1, 1 and 1 only, right? And what is the determinant? Determinant is also 1. So for this particular matrix as well, you are having the same eigenvalues. So can you conclude that B is I3? Absolutely not. Okay. So conclusion we cannot make that B will be equal to I3. It could be anything else as well. No, it could be this matrix as well, because this matrix is also having 1 1 1 as the eigenvalue, and determinant is also 1. So we cannot conclude what will be B. We just needed to find out the determinant of B, which is coming out to be 1. So how did we find out? So relation between B and A was given. Okay, sir. Can I get the eigenvalues of A? Yes, sir. If I know the eigenvalues of A, then sir, I will be able to determine the eigenvalues of B as well. If I know the eigenvalues of B, then simply their multiplication would be the determinant of B. There you go. Understandable? Very straightforward question. Let's go to the next one. Let A be a 7 cross 7 matrix with characteristic equation. This is the characteristic equation is given. Which of the following statements are true? You need to find out that determinant and all those things. Determinant and trace. 2 lambda to the power 7, 3 lambda to the power 6, plus 4 lambda to the power 4, plus 7 lambda square equals to 16 equals to 0. Can I conclude something? No. First target is take this out. Take this 2 out. So if I take 2 common, so lambda to the power 7 minus 3 by 2 lambda to the power 6 plus 2 lambda to the power 4 plus 7 by 2 lambda to the power 6 plus 16 by 2, 8. So now I can conclude something, right? From here I will be able to conclude. What I will be able to conclude? Just 1 second, come on, mobile. Yeah. So what I was saying, what will be the trace? Trace will be summation of roots, or trace will be the summation of eigenvalues. Summation of eigenvalues. And what that would be equivalent to? That would be equivalent to negative of this vector. Negative of this vector. That would come out to be 1.5. And what will be the determinant? Determinant will be simply the multiplication of all the roots. Basically, this will have 7 roots, no? Lambda 1, lambda 2, and lambda 7. This will have 7 roots. So what will be the multiplication? Multiplication will simply be this value. So this value. But 7 is there, which is odd. Answer will be -8. So determinant is -8, trace is 1.5. Very important question. And a lot of people will mess it up. They will forget this negative positive sign. So always in the summation, that means trace will be 3 by 2 multiplied with the negative sign. Just 1 second. Yeah, sorry for the interruption. Actually, some call came in between. Yeah, so we were solving this question. We found out the value of a trace of A and we find out the value of determinant of A. How did we find out? So sir, this was our characteristic equation. We need to make sure that lambda to the power 7, the maximum power should have coefficient 1. I made the coefficient 1. Then I checked that the very next power, lambda to the power 6, that is having a coefficient of -3 by 2. So negative of this coefficient will be my trace. Right? And the very last value, the very last constant value will represent my determinant. But I need to see this power. Lambda to the power 7 is there. Lambda to the power 7, what does that mean? That means it is an odd power, so minus sign I will put. So determinant will be -8 and trace will be 1.5. That's the answer. Okay. Let's solve this question. It is a good question actually. Basically, we are going to make some conclusion from here. So a matrix A is there. It is having 4 eigenvalues. Matrix A is there. It is having 4 eigenvalues, which are lambda 1, lambda 2, lambda 3, and lambda 4. You need to find out the characteristic polynomial and characteristic equation. What is the characteristic equation? You know that, sir, characteristic equation is nothing but this is equals to 0. This is the characteristic equation. Sir, when I solve this equation, I get 4 roots, right? That means when I solve this particular equation, these are the 4 roots I will be getting. So can I write down lambda 1 minus lambda 2, lambda minus lambda 3 into lambda minus lambda 4? This will be my characteristic equation. What will be the roots of this equation? What will be the roots of this equation? So roots of this equation would be nothing but roots here will be lambda 1, lambda 2, lambda 3 and lambda 4. So this is my characteristic equation. So if I have the roots or if I have the eigenvalues, can I write down the characteristic equation? Yes, sir. Lambda minus lambda 1 multiplied with lambda minus lambda 2. So this will be my characteristic equation. Can you write down the characteristics polynomial? Sir, characteristics polynomial. Sir, we used to show it by p lambda, right, sir? We used to show it by p lambda, and p lambda used to be nothing but sir, this a minus lambda e only, right, sir? And sir, can I write down in this manner that I am writing down lambda minus lambda 1? Basically, I will remove this 0. In place of 0, I will write down p lambda. So this will be my characteristics polynomial. But my question would be, is that correct? Is this answer correct? This is your characteristic polynomial. So this is what you have taught. Determinant of a minus lambda I, determinant of a minus lambda I, this was known to be characteristics polynomial. And when you equate it to 0, this is your characteristic equation. This was your polynomial and this was your characteristic equation. This is what you have taught, sir. So yeah, this is what I have written. When you equate it to 0, let's just say my p lambda was 2 lambda plus 3. This was your p lambda. When I equate it to 0, this is my characteristic equation. This is my characteristics polynomial. When I equate it to 0, let's take it on the next page. What I am saying is that my characteristics polynomial, my characteristics polynomial was 3 into lambda plus 3 into lambda plus 2. What will be this was my characteristics polynomial. What will be from here? What will be my characteristics equation? So that will be nothing but p lambda equals to 0, or what you can say 3 into lambda plus 3 into lambda plus 2 equals to 0. So from here what you can get lambda plus 3 into lambda plus 2 equals to 0. So this is your characteristic equation. This is your characteristics equation. And what is your characteristics polynomial? This is your characteristics polynomial. So is this p lambda? Just compare. Is this value p lambda? No, p lambda is this much. What does that mean? It may have some constant factor as well. No, so this is something that I want to tell, that here it may have some constant factor as well, which is k. So if you know the eigenvalues, then you can write down the characteristic equation very easily. But if someone says write down the characteristics polynomial, write down the characteristics polynomial, then what you will say? Let's just say value was 1, 2, 3, 4. So what will be the characteristics equation? The characteristics equation would have been lambda minus 1 multiply with lambda minus 2 multiply with lambda minus 3 multiply with lambda minus 4 equals to 0. What will be your characteristics polynomial? Lambda minus 1 multiply with lambda minus 2 multiply with lambda minus 3 multiply with lambda minus 4, but that value multiply with the constant factor k. Is that understandable to you or not? If you know the equation, that doesn't mean you know the characteristic polynomial as well, because it may have some constant factor that you don't even know. So this was our characteristic polynomial, because 3 can go outside. But this was our characteristic equation. But if I need to write down the characteristics polynomial, it may have some constant factor. The constant factor 3 is there. This constant factor 3 is there, which did not appear here. A very important point, very, very important point, that using the characteristics equation, you can never write down the characteristics polynomial. But using the characteristics polynomial, you can write down the characteristic equation for sure. Just put p lambda equals to 0, you will get the characteristic equation. But if I am having the characteristic equation, you are writing down the characteristic polynomial, but there will be a constant factor for sure. Okay. So this is a concept building question just to solve next particular problem. This question you need to solve. A is a 4 cross 4 matrix whose characteristics polynomial is given. B is defined as this. Which of the following statements are true? You need to find out the trace of A. You need to find out the determinant of A. Then you need to find out the value of A inverse. Then you need to find out the determinant of B. This is the question that is being asked. Is that clear to you? Okay. So shall we get started? Characteristics polynomial is given. What is given? Characteristics polynomial is given. So can I get the characteristic equation? Yes, sir. I can get the characteristic equation by simply putting p lambda equals to 0. So, sir, if I put this equals to 0, what I will be getting? So, sir, from here I need to make sure one thing, that coefficient of lambda to the power 4 should be 1. So, lambda to the power 4 plus 1 by 2 lambda square plus 1 by 2 equals to 0. So, this is my equation. From here, sir, how this equation could be written? Lambda to the power 4 plus 0 lambda to the power 3 plus 0.5 lambda square plus 0 lambda plus 0.5 equals to 0. This is how the equation would be written. So what will be the trace? Trace of A. Sir, after lambda to the power 4, whatever the next coefficient is there, whatever the next power is there, that is lambda to the power 3. Now what is the coefficient of lambda to the power 3? That is 0. That will come with a negative sign. So minus 0 is nothing but 0 only. So what is the trace? That is 0. And what is the determinant? Sir, whatever the last constant value is there, 0.5. Then, sir, I need to see the sign. Then I need to see the maximum power. That is even. So positive sign would come up. So determinant of A is 0.5. This is also correct. Can I find out the value of A square? Yes, sir. This is the characteristic polynomial that is given, right? So since this is given, what does that mean? Sir, 2 lambda to the power 4 lambda square plus 1 equals to 0 is given. So what I can do, sir? In place of lambda, I can put A, right? Now what I can do, I can multiply with A inverse on both of the sides. So if I multiply with A inverse, then what it will become? A inverse into A will become I. So this will become 2A to the power 3. This will become A only, and this will become A inverse. So what is the value of A inverse you are getting? A inverse we are getting is minus 2A cube minus A. So this is the value of A inverse that we are getting. This is also correct. Find out the determinant of B. This is the question. Rest all were just simple things. Find out the determinant of B. Do it on your own. Try it on your own. So what is B? B is nothing but 2 to the power 2A to the power 8, then A to the power 6, then 2A to the power 5 plus A to the power 4 plus A to the power 3 plus 4A plus 3I. 4A plus 3I. This is your B, right? One thing I already know, that this particular thing is equal to 0. What do I know? that 2a to the power 4, 2a to the power 4 plus a to the power 2 plus I is equal to 0. So can I use it somewhere? Basically, I want to make this form. If I am able to make this form here, then I will be able to reduce the expression. No, this expression is looking very much big. So I want to reduce it. So what I thought here is that let's take a to the power 4 common. So what I am getting? 2a to the power 4 plus, then what I am getting? A square. Then I need I. What do I need? I. Can I get I from here? Yes, sir. You can get I from here. Plus, what it is? 2a to the power 8 plus a to the power 6 plus a to the power 4. So this term I have taken, this term also I have taken, this term also I have taken. Now there is 2a to the power 5. So I thought that if I take a to the power 4 common, if I take a common, why I am taking a common? Because I know that inside I will get to do 2a to the power 4. This factor I am considering. If I take a common, then I will get 2a to the power 4 plus this will become a square plus 4i plus 3i. That is coming out to be b. Is that clear to you or not? 2a to the power 8, a to the power 6, a to the power 5, a to the power 4, a to the power 3, a to 4a plus 3i. So a to the power 4 I have taken common. So 2a to the power 4 plus a square plus I from here I have taken. Then 2a to the power 5. So this is a. Then 2a to the power 4 plus a square plus 4i plus 3. Now I know that this particular thing is 0. What I can do here? What I mean to say is that I know that 2a to the power 4 plus a square plus I is 0. What I can do about this particular thing? 4i could be written as I plus 3i. 4i could be written as I plus 3i. Say yes or no? So 2a to the power 4 plus a square plus I. This will also be equals to 0. This will also be equals to 0. So what I can write? A to the power 4 multiply with 0 plus a multiply with 0 plus 3i plus 3i. This is my b. So what I am getting? B equals to a to the power 4 into 0 will be 0. This will become 3a. 3i plus a will become 3a and this will be 3i. This is the value of b you are getting. This is your matrix b. Matrix b. Is that clear to you? This is my matrix b. So I just simply used it. And this is how I reduced it. Here I thought of taking a to the power 4 common. This is the factor I am getting. Just I used this a to the power 4 here. Then a to the power a I have taken common. Then 2a to the power 4 plus a square plus 4i I was getting, but I plus 3i. Okay, so this will become 3a plus 3i. So 3a plus 3i. This was the scenario I was getting. So 3a plus 3i, that is I am getting. What I need to find out? I need to find out the determinant of b. So determinant of b would be nothing but this value, right? So can I take out 3? If I take out 3, power 4 would come. How did I write down this step? I hope you are able to understand how this step came. How this step came. K into some matrix C, determinant would be k to the power n, determinant of C. This is the identity that I am using. So what is A here? A is 4 cross 4. I will also be 4 cross 4. Right? I is identity matrix of order 4 cross 4 only. So it will also be 4 cross 4. This will also be 4 cross 4. So if you are taking 3 outside, so this A plus I will be a matrix of 4 cross 4 only. So if you are taking 3 outside, so 3 to the power 4 will come up. So what is your target now? Target is, now what is my target? My target is finding the determinant of A plus I. This is what I need to find out. What I need to find out? Determinant of A plus I. So I am assuming that there is a new matrix C which is A plus I. Now I know one thing, that A is having the eigenvalues of lambda 1, lambda 2, lambda 3 and lambda 4. Why is that so? Because it can have 4 eigenvalues. It is 4 cross 4. So it is having eigenvalues of lambda 1, lambda 2, lambda 3, lambda 4. So what will be the eigenvalues of C? So that will be lambda plus 1, lambda 2 plus 1, lambda 3 plus 1 and lambda 4 plus 1. And what I am supposed to find out? I am supposed to find out the determinant of C. So that will simply come out to be this value, lambda 2 plus 1, lambda 3 plus 1 and lambda 4 plus 1. So sir, what I can do is that I can solve this equation. I can solve this particular equation. From there, I can get the value of lambda 1, lambda 2, lambda 3 and lambda 4. Once I get this equation, then once I get these values, then I will add plus 1 there and I will get the value of determinant of C. Then I will put it here, I will get the answer. Try finding these values. Lambda 1, lambda 2, lambda 3, lambda 4. Solve this equation and try finding these values. Lambda 1, lambda 2, lambda 3, lambda 4. They will be complex. So first you need to get the roots. Sir, if I know the roots of A, that means I would know the roots of, if I know the eigenvalues of A, then I know the eigenvalues of C as well, because C is nothing but A plus I. So their eigenvalues will be nothing but lambda plus 1, lambda plus 2, lambda plus 3, sorry, lambda 1 plus 1, lambda 2 plus 1, lambda 3 plus 1, lambda 4 plus 1. So I know these eigenvalues as well. I need to find out the determinant of C, because what is my target? My target is determinant of C would be nothing but determinant of A plus I. So that means this is the value I need to find out. So as of now, my matter of concern is that I am supposed to find out this value. This is what I am supposed to find out. This is my target. If I am able to get this value, then your job is done, because this value is nothing but a determinant of A plus I. This is something I need to find out. Now we have the characteristics equation of A, right? We have characteristics polynomial. We have the characteristics polynomial of matrix A. What is that? Characteristics polynomial of a matrix A. Sir, that is given as P lambda. And sir, that is given as 2 lambda to the power 4 plus lambda square, 2 lambda to the power 4 plus lambda square plus 1. Can I write down the characteristic equation of A? Can you write down the characteristics equation of A? Yes sir, characteristic equation of A will be, sir, lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3 and lambda minus lambda 4 equals to 0. Say yes or no. This will be the characteristic equation. Why is that so? Because I am having 4 roots. From here, can I find out, from characteristic equation, can I find out the characteristics polynomial? So, from characteristics equation, can I find out the characteristics polynomial? Someone would say that yes sir, you can find out. Just make sure one thing, in characteristics polynomial, some constant value k can also come up. So sir, simply this will be your answer. Why you are writing down again and again, sir? Simply this will be your answer. This will be your characteristics polynomial. इतनी देर में तो लिख ही देता यार. So this will be your characteristics polynomial. My matter of concern is what will be the value of k here. If I only consider this particular thing, lambda multiply with lambda multiply with lambda multiply with lambda. So if I solve this equation, what I will get? If I solve this much part, I will get lambda to the power 4, then plus something lambda to the power 3, or whatever it is, I don't know, something I will get. But I am pretty sure that this will be lambda to the power 4 only, because lambda is having maximum power 1 here, lambda is having maximum power 1 here, lambda is maximum power 1, maximum power 1. So if lambda multiply with lambda multiply with lambda multiply with lambda, what you will get? Lambda to the power 4. And all are having coefficient of 1. 1 multiply with 1 multiply with 1 multiply with 1. So lambda to the power 4 you will get. That means what you will get? K lambda to the power 4 plus something here lambda to the power 3 something lambda to the power 2, whatever it is, I don't care. This can be compared with this. So from here value of k has to be 2. So your characteristics polynomial of matrix A could be written as 2 into lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3 and lambda minus lambda 4. Say yes or no. And p lambda value you already know. This value you already know. Is that clear to you or not? The very important part is this 2. I know the roots, sir. Roots are lambda 1, lambda 2, lambda 3, lambda 4. I know the roots. Okay. If I know the roots, I know the characteristic equation as well. This is the characteristic equation. If you know the characteristic equation, do you know the characteristic polynomial? Yes, sir. Characteristic polynomial also I know, but there will be a constant factor k. Sir, what will be the value of that constant factor? The value of that constant factor I don't know as of now. Then what I saw that, sir, characteristics polynomial, this is how I can write down. And characteristics polynomial is given in the question as well. From there I got to know that value of k will come out to be 2. Why it is coming out to be 2? Because whatever the equation that I wrote down, when I compared with the equation that is given, lambda to the power 4 is having a coefficient of 2. And I am having a coefficient of k. That means k is equals to 2. So this is my characteristics polynomial. In this characteristics polynomial, if I put lambda equals to minus 1, if lambda equals to minus 1, what I will get? If I put lambda equals to minus 1, so this will become p of minus 1, that will be equated to 2. In place of lambda, you will put minus 1, minus lambda 1, minus 1, minus lambda 2, minus 1, minus lambda 3, minus 1, minus lambda 4. Do you understand why did I put minus 1 here? Because now what I will do, I will take minus sign outward. From here as well, I will take minus sign outward. From here as well, minus sign outward. From here as well, minus sign outward. So minus 1 multiply with minus 1, multiply with minus 1, multiply with minus 1. What it will become? Plus 1. And if you are taking minus sign outward, what you are going to get? From here, what you are going to get? We don't have any page. In the end as well, we don't have any page. So what do we do now? We are lacking the page, guys. So I will have to push it a bit downward. Okay, because we don't have the page. In this slide, I can have maximum 50 pages only. So what is the value of p of minus 1? P of minus 1 I am getting. P of minus 1. So this is 2 only. Then minus sign I am taking outward. So what I am getting? Lambda 1 plus 1, lambda 2 plus 1, lambda 3 plus 1, and lambda 4 plus 1. So that is equivalent to p of minus 1. Can you find out the value of p of minus 1? What is p of lambda? P of lambda is nothing but 2 lambda to the power 4 plus lambda square plus 1. What will be the value of p of minus 1? Sir, p of minus 1, if I put minus 1 here, this was the value only, no? Yes. So what will be the value of p of minus 1? If I put minus 1 here, then if I put minus 1 here, that is coming out to be 4. So p of minus 1 is nothing but 4 only. So from here, from this equation, can you let me know the value of lambda 1 plus 1 multiply with lambda 2 plus 1 multiply with lambda 3 plus 1 multiply with lambda 4 plus 1, that will be equated to 4 divided by 2, that will be equated to 2 only, right? So this is the value that we are getting. And what is this lambda plus 1 and all those things? Let's call this some equation. Forget about it. So lambda plus 1 into lambda 1 plus 1 plus lambda multiply with lambda 2 plus 1. What is this? This is nothing but determinant of C. So this is nothing but determinant of C, which is equals to the determinant of A plus I. So what will be the determinant of B that you are getting? So determinant of B that we are getting is, sir, nothing but determinant of B. Determinant of B is 3 to the power 4 multiply with determinant of A plus I multiply with 2. Okay, so this will be 81 multiply with 2, 162. Absolutely brilliant problem. If this kind of questions are coming, then hardly 1 out of 1,000 students would be able to solve it in the examination. So answer is 162. This is wrong. Why I put 324 here? Because I know that those guys who have done very well in JEE mathematics, they would be able to think, but they will forget this factor too. I'm pretty sure they would have forget this factor too. What they would have done? Characteristics polynomial, they would have done lambda minus lambda 1 multiply with lambda minus lambda 2 multiply with lambda minus lambda 3 multiply with lambda minus lambda 4. Then they would know that, sir, I need the value of lambda 1 plus 1. That means in place of lambda, I need to put minus 1. Then they would put it and they would get the answer. P of minus 1 value is 4. From here, they would get P of minus 1 is 4. Then they will multiply 3 to the power 4 with 4. So 81 into 4, what that would be? 324. Yes, sir, this is the answer. 324 is the answer. So this is what a lot of people would have done, right? But always remember, that's why I took this question, that if I know the roots, which are lambda 1, lambda 2, lambda 3, lambda 4, then I know the characteristics equation for sure. That would be lambda minus lambda 1 multiply with lambda minus lambda 2 multiply with lambda minus lambda 3 multiply with lambda minus lambda 4. I know the characteristic equation for sure, but characteristics polynomial will have a constant factor as well. That constant factor could be there. Why is that so? Using this example, right? Using this example, I can sense that, yes, sir, here characteristics polynomial was given, which was having a constant factor of 3. But when I wrote down the characteristic equation, then I was not getting this constant factor 3. That means from this equation, if I write down the characteristic polynomial, from here if I write down the characteristic polynomial, then characteristic polynomial for me would be lambda plus 3, lambda plus 2, but here some constant factor would come up. So how will I find out the value of this constant factor? From here I will find out that, sir, here what was the value given? 3. That means k was 3. So similarly, here as well, in this problem as well, what we did, this much analysis was easy for us. Then we got to know that A is having 4 eigenvalues. Then I can write down the characteristic equation of A. The way I wrote down the characteristic equation of A, from that characteristic equation, can I get the characteristic polynomial? Yes, you can get, but k would be there. Now, can I get the value of k? If I compare with the actual expression is saying that lambda to the power 4 is having a coefficient of 2. That means k value has to be 2. So this is the value of k I am getting. Now my target is getting this value, lambda 1 plus 1 multiply with lambda 2 plus 1 multiply with lambda 3 plus 1 multiply with lambda 4 plus 1. What does that mean? That means if I am having this equation, in this equation if I put lambda equals to minus 1, then I can take minus sign outward, then 2 into 1 plus lambda 1, 1 plus lambda 2, 1 plus lambda 3, 1 plus lambda 4, then this is something I can get, right? This is equated to 4 only. Why it is equated to 4? Because it is equivalent to p of minus 1. So from here, this is the value that we are getting, that is coming out to be 2. So 3 to the power 4 multiplied with 2 is 162. That is the answer. Say yes or no. Understandable? Very straightforward. Okay. So we are just solving the problems. More questions we are going to solve. But before that, let's understand a very simple concept. Very, very straightforward concept that you already know. So can you write down the characteristic equation of this? Yes, sir. Lambda square minus, what is the trace? 2. What is the determinant? 2. Right? 1 minus minus 1, determinant is 2. So this will be the characteristic equation. Can you solve it? Yes, sir, I can solve it. What is the value of lambda you will get? Minus b plus minus under root b square minus 4ac upon 2a. Right? So 2 plus minus 2j divided by 2. So value of lambda you are getting 1 plus minus j. That means it is having 2 eigenvalues. 1 plus j, 1 minus j. Now what is the meaning of, sir, real matrix? Real matrix means all the elements are real. All elements are real. Okay? All elements are real. This is the meaning of a real matrix. Real matrix means all the elements of this matrix A are real. From there we are getting eigenvalues which are complex. Eigenvalues which are complex. These values are complex. Right? We have seen a lot of examples where eigenvalues were real. Eigenvalue was real. So if there is a real matrix having real elements, then eigenvalues could be complex as well. They could be real as well. But if they are complex, then they will be complex conjugate. They will be complex conjugate. Can I say that lambda 2 is simply lambda 1 conjugate only? If you take the conjugate of this, j will be replaced with minus, j will be replaced with plus j. So for a real matrix, you can get complex eigenvalues. Surely you can get complex eigenvalues, but whatever the complex eigenvalues that you are getting, they will be in the conjugate form. So if I say that I am having a matrix A which is having 3 eigenvalues, one eigenvalue is 2 plus j, other eigenvalue is 3, can I find out the third eigenvalue? Yes, sir. It is a real matrix, that means third eigenvalue will be simply the conjugate of this, which will be 2 minus j. So these 3 will be the eigenvalues. Is that clear to you or not? So these kind of question could be asked in the examination, that only one complex value they will mention, one some other value they will mention, and then other thing you need to comment. Because if this I know this complex value which is 2 plus j, then other one would be 2 minus j only. Understandable? Now what about the complex matrix, sir? Complex matrix. What is the meaning of complex matrix? Complex matrix means one of the elements should be complex. One of the elements should be complex. Here real elements are also there. Here complex elements are also there. But only one element you need complex. One of the elements should be complex. One of the element should be complex. Only one complex element is there, no? That means it is a complex matrix. Okay. So when I solve this, these are the eigenvalues I am getting. So what all eigenvalues I am getting? What all eigenvalues I am getting? 2 plus I, 3 minus I, and 4. So are they in the conjugate? No conjugate. No conjugate. So basically whatever the concept that we have studied here, that they will be in the conjugate, they will be in the complex conjugate, this works only for real matrices. So what is the conclusion, sir? What you are saying? Conclusion is that matrices could be real as well, it could be complex as well. If we find out the eigenvalues, so sir, if we find out the eigenvalues in both of the cases, then sir eigenvalues could come out to be real as well or complex as well. It could be real as well or it could be complex as well. We have seen multiple examples, right? Here as well, sir, it could be real as well, it could be complex as well, because eigenvalue came out to be real as well and complex as well. Real or complex. But sir, here there is a special case. Here there is a special thing that, sir, if it is coming out to be complex, in case of real matrices, if it is coming out to be complex, then they will be in the conjugate. But here it is not necessary to be conjugate. They may be conjugate, they may not be conjugate, not necessary conjugate. Not necessary conjugate. So here they are surely conjugate, here they may be conjugate, may not be conjugate. Is that understandable to you or not? Okay. So we will solve a question related to it. Again, what is the conclusion? Matrices could be real as well, matrices could be complex as well. Both of the matrices can have both kind of eigenvalues. It could be real as well, it could be complex as well. But in case of real matrices, if you are getting one complex eigenvalue, then its conjugate will also be present. Is that clear to you? So using this question, we will using this property, we will solve a question. But let's write down the conclusion. What is the conclusion? For real matrix, if complex number a plus iota b is an eigenvalue, then its complex conjugate a minus iota b will also be an eigenvalue. For complex matrix, there is no such restriction. Eigenvalue need not appear in conjugate pairs. Very simple thing, very straightforward. Say yes or no. Very straightforward it is. Real matrices, if you are getting complex eigenvalues, then if you are getting a plus iota b, then a minus iota b will also be an eigenvalue. But for complex matrix, there is nothing like that. Understandable? What is given? A is a real 3 cross 3 matrix. A is a real 3 cross 3 matrix. One of the eigenvalue is 4 plus 3i. So if A is a real 3 cross 3 matrix, here I am doing the solution. Okay. If A is a real 3 cross 3 matrix, then how many eigenvalues it will have? Sir, it will have lambda 1, lambda 2 and lambda 3. 3 eigenvalues it will have. Sir, one of the eigenvalue is given, that is 4 plus 3i. Since it is a real matrix, sir, I know that other eigenvalue will be nothing but 4 minus 3i. I can write down I as well, I can write down j as well. Okay. Sometimes it is written as j, sometimes it is written as I. Don't get confused. Here I am writing down I. Okay. So which of the following statements are true? Lambda 1 I know, lambda 2 I know. Do I know the lambda 3? I don't know lambda 3, but I am pretty sure that it will be real. 101% it will be real. Why is that so? If it was complex, let's just say if lambda 3 was 2 plus 3j, then another eigenvalue has to be there which will be 2 minus 3j. Because if it is a real matrix and you say that a plus iota b is present, then a minus iota b will also be present. But it is not possible. Why is that so? Because it can have only 3 eigenvalues. It can maximum have only 3 eigenvalues. So if it can have only 3 eigenvalues, one eigenvalue I know which is 4 plus 3i, then second has to be 4 minus 3i and third has to be real, because if it was complex, then its conjugate should also be present, which is not possible. You can write down here. Okay, in your rough space you can write down. If you feel like that I will be forgetting it. But here I am just writing down that it is real for sure. 101% will be real. Why is that so? Because if it was complex, then its conjugate also has to be present. But since it is a 3 cross 3 matrix, only 3 eigenvalues are possible. So fourth eigenvalue will not even be there. Is that understandable to you? So lambda 3 has to be real. Okay, so first option. A must have one real eigenvalue and 2 complex eigenvalues. Yes. A will surely have 3 linearly independent eigenvectors. Are they different? Are all of them different? If they were same, then I need to think. But if they are different, lambda 1, lambda 2, lambda 3, all these are different. Say yes or no. Lambda 1, lambda 2 and lambda 3, all 3 are different eigenvalues or not? 4 plus 3i is not equals to 4 minus 3i, right? They are different, no? Someone would say that, sir, they are conjugate, but lambda 1 is not equals to lambda 2. They are different eigenvalues. Okay? So they are different and lambda 3 is also different. So with respect to different eigenvalues, you will get linearly independent different eigenvectors. So it will surely have 3 linearly independent eigenvectors. Say yes or no. It will surely have 3 linearly independent eigenvectors. Understandable? A may have repeating eigenvalues? Absolutely not. And now what they have given? Determinant of A equals to 21, right? So what will be the real eigenvalue? So determinant of A is 21, then this will be 4 plus 3i, this will be 4 minus 3i, and the real eigenvalue is lambda 3, that is 21. What is the multiplication of both of them? I hope you know. It is a square plus b square. Okay, a square plus b square, a square plus b square. So 4 square is 16, 3 square is 9, so it will be 25. So 25 into lambda 3 equals to 21. So lambda 3 will come out to be 21 by 25. Okay, so this will be the value. So this option is also wrong. Is that clear to you? So this kind of question could be asked. 3 cross 3 matrix is there. One of the eigenvalue they have mentioned. Other eigenvalue you already know, which is 4 minus 3i. And third one you know that it will be real. All three are different. This is already real, so it will be different than the complex value. Lambda 1 is not equals to lambda 2 is not equals to lambda 3. And surely it is not equals to lambda 3. Right? Understandable? All three are different. If all three are different, then what will happen? If all three are different, then they will have 3 independent eigenvectors. If they were same, then I would have to think that what will be the geometric multiplicity and all. But here, different eigenvalues will have different eigenvectors. I don't need to think. So they will have 3 linearly independent eigenvectors. Can they have repeating eigenvalues? No. And if determinant of A is given, that means multiplication of lambda 1, lambda 2, lambda 3 is given. 4 plus 3i, 4 minus 3i multiplied with lambda 3 will be equal to 21. So value of lambda 3 is coming out to be 21 by 25. Understandable? Let's go to the next question. These two questions are there. Try solving it. Let A be a real 5 cross 5 matrix. Two of the eigenvalues are given, 4 plus 3i and 2 minus 4i. It is given that rank of A is 4, then find the trace of A. Try doing it on your own. Rank of A is given 4, which is less than n, or you can say which is less than 5. From here you can understand that this will be 0. Okay. Now 2 of the eigenvalues are mentioned. A can have 5 eigenvalues, no? 2 of the eigenvalues are mentioned, 4 plus 3i. Then other eigenvalue I already know, it will be 4 minus 3i. Then 2 minus 4i is mentioned. Then other eigenvalue I already know, it will be 2 plus 4i. Now can you let me know what will be this eigenvalue? Sir, it will be a real eigenvalue. If determinant is coming out to be 0, what does that mean? That means lambda 1, lambda 2, lambda 3, lambda 4 and some lambda 5 will make the determinant 0. If the determinant is 0, then you know that 0 has to be one of the eigenvalue, no? Because nullity of A, if a rank is 4, then what will be the nullity of A? Nullity of A is 1. And nullity of A represents the number of independent eigenvectors corresponding to lambda equals to 0. So if nullity is non-zero, if nullity is greater than or equals to 1, that means lambda equals to 0 is present. Lambda equals to 0 is present. So third eigenvalue is lambda equals to 0. Sorry, fifth eigenvalue is lambda equals to 0. So if you know all these eigenvalues, what you are supposed to find out? You are supposed to find out the trace of A. What is the meaning of trace of A? You need to add all of them. 2 minus 4i plus 2 plus 4i. So if I add all of them, what I will get? 12. So answer is 12. Okay, this is the answer. These kind of questions are asked in GATE examination actually. Okay, don't think that sir these kind of questions will not be asked. These are important with respect to GATE examination. Okay, now next question. Let A be a 7 cross 7 matrix 1 1 1 1 2 2 3 4. What is the minimum possible number of linearly independent eigenvectors and what is the maximum possible number of linearly independent eigenvectors? I think you should be able to tell what will be the answer. So 1 1 1 2 2 3 4. With respect to these same eigenvalue, at least one I will have, at least one linearly independent eigenvector I will have, or maximum 3 I will have, right? At least 1 or maximum 3. At least 1 or maximum 3. And here at least 1 or maximum 3, right? And here one independent eigenvector will have, and here one independent eigenvector will have. So total minimum will be 4 and maximum will be 3 plus 3. Sorry, maximum will be 2, no? Why 3? Because this value is repeated twice. Here arithmetic multiplicity of 1 is 3. So what could be the geometric multiplicity of 1? That has to be less than or equals to 3, right? Because AM is greater than GM. arithmetic multiplicity of 2 is 2. So what will be the geometric multiplicity of 2? That has to be less than or equal to 2. So minimum I can have 1, maximum I can have 3. So here 4 and here 7. So this is repeated thrice. With respect to these eigenvalues, minimum I will have one independent eigenvector. Minimum I will have one independent eigenvector. Here surely I will have one independent eigenvector. Here surely I will have one independent eigenvector. So total 4 eigenvectors I will have. That is the minimum number, and maximum linearly independent eigenvector that I can have is 7. That's it. Is that clear to you? Okay. So this lecture is done. Next lecture we will start solving the problems only. So this is the first part of eigenvalues and eigenvector. I hope you are enjoying the depth of the lecture. Okay. Otherwise this particular topic would have been taught in some 2 hours. Very simple thing you could have been taught. Determinant of a minus lambda equals to 0. Find out the value of lambda. Find out the eigenvector. Chapter is done. But we are seeing the actual concept, actual depth, that no matter how tough problems they are framing, we will be able to solve it. If they are framing this kind of problem as well, then also we will be able to solve. Okay. So let's meet in the next lecture. There we will solve some problems and we will see some more concepts. Okay. Thank you very much.